Okay, welcome to Intro to Programming. This will be our first webinar. The first thing I have to do is read this webinar disclaimer. The WebEx service includes, this WebEx service includes a feature that allows audio and any documents and other materials exchanged reviewed during the session to be recorded. By joining the session, you automatically consent to such recordings. If you do not consent to the recording, please do not join or participate in the session. This WebEx service is intended to supplement the classroom experience. Duplication or redistribution of lecture capture recordings is prohibited without appropriate consent. Okay, that's kind of like something I have to just do right up front. Now I guess we can begin. There we go. Okay, Chapter 1. We'll start right off at the very beginning. What is a computer? This particular Introduction to Programming course presumes that nobody has previous experience in computing or programming, which is probably a bad presumption because many students do have some exposure to computers, obviously, and even computer programming. So we are going to go ahead and start right at the very beginning and identify what a computer is. A computer is a programmable electronic device that can input, process, and output data. And by outputting data, you can also store it as well. If anybody's on, please mute your phone so there isn't any background noise. So that's a computer, basically something that gets input, processes the input, and then produces output. The output can be in the form of a report. It can be to a screen, or it can be outputted to storage for later usage. Here's a diagram that kind of describes how the computer does work. If you have input, what are some input devices? Could be a keyboard, could be a microphone, could be a mouse. These are all input devices, and you would input data into the computer's random access memory, also known as RAM. Everything gets entered into RAM before it can be processed. If you want to enter or load a program comes from your storage and gets loaded into RAM. Let's say it's Microsoft Word. You would load Microsoft Word into RAM. You could go ahead and enter data. Everything goes into RAM. And when you need to process things need to be processed via random access memory. Once it's done processing, the data turns into information, and it gets sent to some output device, such as a printer or a monitor. The key concept behind this slide is that everything goes through RAM. So it's kind of important that you have enough RAM in today's world with very large amounts of data and very large programs that do need to get loaded into RAM. It's a good idea to have an awful lot of RAM space when you are purchasing a computer. By the same token, with videos and audio, a large amount of storage capacity is also a good consideration. A large C disk, they're getting up close to 1 terabyte now, so that might be something that would be worthwhile in getting. Oh, don't tell me this froze on me here. Okay, my screen just froze. All right, you know what I'm going to have to do, guys? I'm going to have to reboot. So you guys can stay put. I have to reboot because my computer froze, and I'll re-log in, and I should be rejoining probably within a minute or two. So bear with me until I come back in. Okay, I'm back, guys. Everybody still there? Julio, Mark?
Yes, I'm still here.
Okay, good. Thanks for hanging in there. And you know what? I'll tell you what I think the problem is that causes that, and that is my cursor. You know, I have this app that illuminates my cursor, and you may have seen that in the presentation. And I believe that cursor app causes this computer to freeze. All right. I don't know what happened to my. All right, I'll go get it again. Okay, so let's try it again. Let's. Oh, I got to see if I'm recording in case anybody is. Okay, it looks as though it's recording still. So. Okay, here we go. We're going to do this one more time. We'll go to previous. I'm going to stick with this cursor. I had been given some suggestions that my cursor could not be seen during these WebExes. So I went out and I got that app that illuminated it in purple. And ever since I got that, it has, I believe, caused my WebExes to freeze on me. So I'm not going to use that. We'll see if we can get through this without the illuminated cursor. And that means I'll just have to go slow with my cursor so that you guys can see where I'm pointing. All right, I think we were done with this slide here. We talked about input, process, output, and everything has to go through RAM. In class, I used a little diagram here to illustrate that when you boot up Windows, for instance, Windows is stored over here on your hard disk. It needs to get loaded into RAM. And then as you bring in Microsoft Word and browsers and other applications, everything needs to be brought into RAM. If there's any kind of calculations that need to be done in these applications, such as Word, Excel, or PowerPoint, the calculations are done over in the CPU, which is the central processing unit. The central processing unit has three major components. It has a control unit, it has an arithmetic logic unit, and it has a system clock. If you have to do a calculation like 7 times 3 over here in an application running in RAM, it will then get sent over to the CPU. The control unit is like the cop, and the cop will conduct traffic. And the control unit will determine who's been waiting the longest to do a calculation. And then once my 7 times 3 has waited its turn, it will then pass that on to the arithmetic logic unit, the ALU, and it flips the bits and calculates 7 times 3, comes up with 21, and then passes it back into the application that requested it. The control unit uses the system clock to determine who's been waiting the longest. So that's essentially, in a nutshell, how things are processed. But the key ingredient here is this RAM thing. You need to make sure you have plenty of RAM in order for you to do your processing. The CPU, you might want to have a powerful, fast chip if you have a need for very fast lightning calculations. And obviously a lot of data, you would need to have a very large hard disk. A computer consists of CPU, memory, hard disk, floppy disk, monitor, printer, and communication devices. These are all the pieces to a computer. The CPU we just talked about, that's the central processing unit. That's the brain of the computer. It retrieves instructions from memory and executes them. The CPU speed is measured in megahertz, with the megahertz equaling 1 million pulses per second. The CPU has now been improved continuously, and if you buy a PC now, you can get an Intel Pentium 4 processor at 3 gigahertz, and a gigahertz is a billion pulses per second. So your CPU is how fast this computer thinks. Memory, that's RAM, that's random access memory. A key component of RAM, or a concept of RAM, is that it is considered to be volatile. Volatile memory means that it goes away when the power source goes away. If you unplug your computer, everything in memory, everything in RAM memory is lost. If you want to be sure that you don't lose your data, then you need to go ahead and save it onto a hard disk over here in the storage devices. A disk, thumb drive, some permanent storage. That would be non-volatile memory. And then you have your communication devices, your input devices, and your output devices, which I think we kind of know about. Okay, now how is data stored? Data of various kinds, such as numbers, characters, and strings, are encoded as a series of bits, zeros and ones. Computers use zeros and ones because digital devices have two stable states, which are referred to as 0 and 1 by convention. We programmers use zeros and ones, but it's really electronic states. You can also think of it as being on or off, clockwise or counterclockwise. But the concept is it's binary. You can have only two states. It's a lot easier to think of it as zeros and ones. Programmers need not be concerned about the encoding and decoding of data, which is performed automatically by the system based upon the encoding scheme. The encoding schemes vary. For instance, the character J is represented by this bit configuration in 1 byte. A byte has 8 bits, and there are 8 bits in this configuration, and that represents the uppercase J. A small number, such as the value 3, can be stored in a single byte. If a computer needs to store a large number that cannot fit into a single byte, it uses a number of adjacent bytes. No two data can share or split a same byte. A byte is the minimum storage unit. And they give a little example over here where we have a memory address, and it looks as though it's ascending as we go down the slide. And the contents of the memory is what's represented right here. And each one of these boxes represents a byte. So the first box here in memory address 2000 is the uppercase J. Now this is using the ASCII character representation. And just quickly going through this, ASCII is a convention used by computer people around the world. And the convention is essentially to use, if we use these bits going from right to left as powers of 2, this first bit would be 2 to the 0 power, or 1. Then this is 2 to the first power, or 2s. 2 squared is 4, then 8, then 16, then 32, then 64, then 128. This 64-bit right here, this bit right here is like a zone bit that says this is going to be an ASCII character and it's going to be uppercase. These other bits to the right of this zone bit indicate the displacement into the alphabet in powers of 2. So as I said, this is the 1s column, the 2s columns, the 4s, and the 8s. So we have a 1 in the 8 column, and then we have a 1 in the 2 column. So an 8 and a 2 would be 10. And the J is the 10th character in the alphabet. And because this bit says it's ASCII and this bit is off, it says it's uppercase. If we look at the next byte, we have the 64-bit on, and we have the 32-bit on. That says it's ASCII. That says it's going to be lowercase. And then this is the displacement into the alphabet. And we have just a 1 in the 1s column. So that would be the first character in the alphabet, which is the lowercase a. The V would be the 64-bit is on, saying it's an ASCII character representation. The next bit, the 32-bit, says that it is lowercase. And then we have 16, no 8s, a 4, and a 2. 16 and 4 and 2 is 22, so V is the 22nd character in the alphabet, and it's lowercase. Here is another A, and then the number 3. This is a value, so these are character representations. This is not a character. This is a value, and the value is simply the sum of all of the bits and whatever their associated values are. For instance, this is the 1's bit, the 2's bit, the 4, the 8, 16. There's no bits flipped after the 2's bit. So we have a 2 and a 1. So the total value in this byte of storage is 3.
I'm sorry.
And that essentially is how. Nope, go ahead. What do you got?
I lost my video. I've been trying to put it back. All I'm seeing is Kerry Kramer's personal room.
Okay, that is Mark speaking?
Yes, yes.
Okay, and now Julio, are you able to see the video?
The same thing happened to me.
The same thing happened to you?
Yes.
Oh my goodness. All right, so let's just see what the problem is. Okay, I bet you can see it now, right?
Yes. Well, yeah. Now again.
Oh, okay. All right. Yeah. Evidently, when I was frozen, it didn't continue my sharing of the screen. Okay, so just to kind of go through that quickly, now that you've got the slide in front of you, do I need to go through this again? Because you weren't seeing what I was showing here, but here is 1 byte of storage. This particular bit right here is the 64-bit. And the 64-bit is on, which says this is going to be an ASCII character. The next bit, which is a 32-bit, these are powers of 2 going from right to left. The 1s, the 2s, the 4s, the 8s, 16s, 32, 64, and 128. So the 64-bit is on, the 32-bit is off. The 64-bit says that this is going to be a character value. The 32-bit, which is off, says it's going to be an uppercase. And then these remaining bits identify the displacement into the alphabet. So what do we have here? We've got no 1s, we've got a 2, we've got no 4s, and we have an 8. So an 8 and a 2 adds up to 10. So J is the 10th character in the alphabet, and it's uppercase because this bit is off. The next byte, we have the 64-bit on, which says that it's going to be a character, an ASCII character, and it is going to be lowercase because this bit is on, and the remaining bits identify the displacement into the alphabet, and it's the first character in the alphabet. It's lowercase a. V, on the other hand, would be an ASCII character here, a lowercase because this bit is on, and then we have a 2, a 4, no 8s, and a 16. So a 16 and a 4 and a 2 adds up to 22. So V is the 22nd character in the alphabet. This is how your character data is being stored. Here's another A, identical to this one up here. But the 2004 memory address doesn't have character representation here. It's an actual value. And this value 3 can be simply understood to be whatever the representation is of these bytes, of these bits. The 1's bit is on, the 2's bit is on, the 4 is not on, the 8's not on, the 16, the 32, the 64, and the 128 are all off. So we just have the 2 and the 1 bit on. The 2 plus 1 is a total of 3. So this byte of storage is storing the value 3. That essentially is how the data is stored in computers using these types of representation, character data and numeric data. Storage devices, I'm sure you guys are aware of. This is CD drives and floppy disks and thumb drives, and the data that's stored on those drives is stored the same way as what we just described using the ASCII values and the numeric values. Output devices are monitors, printers. Excuse me. Monitor resolution and dot pitch. Resolution is the screen resolution, and it is measured in pixels. And the number of pixels in the horizontal and vertical dimensions of a particular display device, such as a monitor. Pixel stands for picture element. It's a combining of two terms, picture and element, and they are the tiny dots that form the image on the screen. A pixel can be comprised of three components: a red component, a green component, and a blue component, an RGB color pattern. And each one of those components can be stored in 1 byte of storage. Don't want to get into too much details on this, but you can store many, many colors in 3 bytes, with 1 byte representing every different shade of red, another byte representing every shade of blue or green, and then the third byte representing every shade of blue, the RGB color scheme. So that's resolution. It's measured in pixels. A common resolution for a 17-inch screen would be, for example, 1024 pixels by 768 pixels high. And that actually is a very low resolution screen by today's standards. They've gotten much, much sharper. The dot pitch is how close these pixels are together, and it's measured in millimeters. The smaller the dot pitch, the sharper the display. Modems have come a long way. I remember the days when we had dial-up modems, and I had a 14.4 kilobits per second modem way back in the 1980s, and it has come a long way since then, and now pretty much every household does have a high-speed either DSL or cable modem in their premises. Okay, computer programs are known as software and instructions to the computer. You tell a computer what to do through the programs. Without programs, a computer is an empty machine. It can't do anything. Computers do not understand human languages, so you need to use computer languages to communicate with them. And then programs are written using programming languages. My very first programming language, my second language, actually, my first was BASIC, but after BASIC, I learned Assembler, the assembly programming language. And it's a very, very low-level language. It's working with a lot of bits and bytes, and it's very tedious. The good side of learning assembler is you do understand exactly what's going on inside your computer. Nowadays, you really don't have to focus too much on very low-level languages, because the higher-level languages are much more popular, and they are very, very powerful. And because computers have gained so much power, you can use high-level languages to solve problems. 30, 40 years ago, the computers weren't that robust and that powerful, so you had to write in very low-level languages, such as assembler. Here's an example of assembly language. Here would be the instructions: add register 3 and register 2 and register 1. And this is your instruction, the add instruction. That actually gets directly translated over into machine code and gets stored in a series of zeros and ones. Higher level languages are English-like and easy to understand, and they're relatively easy to learn. For example, the following is a high-level language statement that computes the area of a circle with a radius of 5. And this you can tell area is equal to pi, which is over here on the right-hand side, r squared. Area equals 5 times 5 times 3.1415. So that the radius is 5, and when this calculation gets done, it goes from right to left. So wherever there's an equal sign, that's actually an assignment operator, which says do this calculation and then take the result of this and store it into an area in storage called area. This is an example of a high-level language, which is a lot easier to understand than the previous one that was just zeros and ones. Here are many other popular high-level languages. Java is the one that we're going to be using in this class. It was derived from originally the C programming language, and then that evolved into C++, which allowed for object-oriented programming, and now Java is a very, very powerful programming language. And the biggest, well, there are many different important features of Java, but one of the big ones is that it works with the internet. And many applications are now being developed for the internet, so Java looks to be the strategic language for today. Now, a program is written in a high-level language called a source program. That area equals 5 times 5 times 3.14, that is source code. It's written in a source program, and you need to go ahead and convert that from source code over into machine code. And then the machine code is what gets executed. The translation can be done using another programming tool called an interpreter or a compiler. So for example, in our area equals pi r squared example, you can take this and run this through an interpreter, and it will produce output. An interpreter is a little different from a compiler because an interpreter reads one statement from the source code at a time and translates it into machine code, statement by statement, and executes it right away. A compiler, on the other hand, translates the entire source code into machine code, into a file of machine code, and then that machine code file is then executed. Compiling source code into machine code oftentimes is much faster than an interpreted solution. Here's a diagram that shows you compared to the hardware. And the hardware essentially works with the operating system. We'll think of it as Windows. Application programs are loaded into RAM, and they work together with the operating system. And the user typically works with the application programs, which work with the operating system, which works with the hardware. The operating system can also work with the user for login purposes, and log off, and things like that. But generally, this is the hierarchy for all of these entities. Why Java? Basically, as I said before, it's the one that is most compatible with the internet, and it is also portable to all different platforms. So Java runs on our cell phones, our smartphones, servers. It runs on desktops, laptops, and large mainframes. I'm not going to get into the Java history. You can read about that in the textbook. Again, I think the most important thing here is that it is architecture neutral, right? We'll run it anywhere. With the Java virtual machine, you can write a program one time and run it on any platform. Back in the olden days, back in the 80s and the 90s, if I wrote a program on a particular computer, it could only run on that computer. If I wanted to take that program and run it on some other device, I'd have to rewrite the whole program. So now Java is portable and architecture neutral. It is very, very flexible. Here's the history of the Java development kit. When you download NetBeans, for instance, along with NetBeans comes the Java development kit, or the JDK. And inside the JDK has all of your tools, your compiler. It has all of your other tools that you can use in developing your solutions. The JDK versions, starting in 1995, started with JDK 1.02, and currently right now we're working with JDK 1.8, which which came out in 2014. It's also known as Java 8 or JDK 8. In this class, we'll be using the Java Standard Edition, the J2SE, and that's where we're developing client-side standalone applications. You can also use J2EE, which is for server-side applications, Java Micro Edition, J2ME, which can be used for mobile devices, and this is our book we'll be using, the first one, the Java Standard Edition. We're going to be using NetBeans, and hopefully both of you or whoever else has joined have been using NetBeans to submit your assignments. There is also Eclipse, which is another IDE. An IDE is an integrated development environment, and the two strategic ones are NetBeans and Eclipse. In this class, we'll be using exclusively NetBeans. Here's a typical example of a program, and I'll just go through the pieces here. This first line here has two forward slashes, which indicates that this is a line comment. And in this line comment, it says this program prints "Welcome to Java." The next line here has a public modifier and then an identifier which says that this is a class, and the class name is going to be welcome. The class starts here at this left curly brace and ends down here at this right curly brace. It's very important that you indent and use this structure when trying to write your code and read your code and leave it for somebody else to go ahead and maintain, because these can be placed anywhere. The compiler doesn't really care, but other programmers reading your code certainly do. So it's important that you put your curly brace on the same line as the welcome, the name of the class, and then directly underneath the P in public, put your closing curly brace. This identifies this particular program as a class. Inside this class, we're going to have a method. These are modifiers, public static, and then void main. This is a method, the main method. We know it's a method because it has parentheses. It has an opening parentheses and a closing parentheses. Inside the parentheses are what's known as parameters. And parameters are separated by commas. In this particular case, the main method has only one parameter. There are no commas in here, so it has one parameter. The parameter is args. That's the name of the parameter, and it is going to be of a string array. That's what this means. We'll talk about this later on in the semester, but essentially this main method gets past a parameter of strings, a string array. Normally, you don't pass it anything, but later on in the end of the semester, we're going to pass an actual string to the main method. So you can go ahead and just use this as your structure: public static, void main, open paren, string, left bracket, right bracket, and then args, close the parentheses, and then open up your main method with another curly brace on the same line as the main method. The main method ends on this curly brace, directly underneath the P in its public. This main method has only one statement. It is system.out.println, and it says "Welcome to Java." This will print "Welcome to Java" to the console. This is a string. It is surrounded in double quotes. So whenever you want to put out a string, it needs to be put out in double quotes. Println here is a method in this library, in the system library. We know it's a method because it has parentheses. It's got an open parentheses and a closing parenthesis. And inside are the parameters. There's only one because there's no commas, and this parameter is a string, and that essentially says pass this string to this little program, this little method called println, and it will go ahead and take it and send it to the console. You can also write code. Instead of using NetBeans, you can also use Notepad and type this code in and use the DOS prompts to do that. I'm not going to spend any time in tonight's webinar on the DOS, but you can follow the instructions in the in-class assignment and just see how that works. That's originally how code was written, and now it has evolved into the integrated development environments, EDEs, such as NetBeans, which makes life a lot easier for all of us. You can also use WordPad. Here's another diagram that identifies your simple program, which says Welcome to Java. It's of the same structure that we just went through. Here's your source code. We wrote it in Notepad, and we store it on some disk. This source code right here is stored on the disk, and then you need to compile this code. Well, there's a program in the Java Development Kit called Java-C, which will compile this welcome class called welcome.java file. If there is a clean compile, it creates what's known as bytecode. And this bytecode looks something similar to this over here. Not necessary to understand that, but just understand that it is bytecode. And then you can run the bytecode by invoking this Java program, which will then run the welcome.java, the welcome.class file. And then you're going to get the result, welcome to Java, displayed to the console. If you have compiling errors, you have to go back in here and re-look at your source code and find out if you're missing a semicolon or parentheses or a double quote or something like that. Here's another diagram. It basically says the same thing that I've been saying, so I'm going to skip over that. And likewise, this is kind of a hierarchy here where the Java Development Kit, which if you look at when you downloaded NetBeans, it will store it on your C disk. And inside the Java Development Kit is the JRE, the Java Runtime Environment, and inside the Java Runtime Environment is the Java Virtual Machine. So you get an understanding of the hierarchy of those three components. Here's a trace. I'm not going to go through that because I just went through it. Welcome with 3 messages and compute expression. I'm going to go over to NetBeans for a moment. And I'm going to execute a program. Where is my NetBeans? Over here. I had this all queued up and ready to go before it froze. I'm going to do File, Open Project. And by the way, all of my assignments, there are examples of what I'm expecting you to do in these sample programs posted in Blackboard. One of the programs for Chapter 1 is, I think, called Simple Arithmetic, right here. Okay, here is a different structured solution than what we've been talking about before. We were writing code in welcome.java and compiling it and creating another file called welcome.class. And then we would run using the Java instruction in the DOS prompt to run the class file welcome.class. Over here in NetBeans, there's a different structure to it. You have a whole bunch of folders within folders and a project, and within a project and packages. Over here, you'll see here's where the source packages are. I called this class Simple Arithmetic, and it's very important that you understand that Java is case sensitive. When you're calling a class, or when you are creating a class, you need to go ahead and put the first letter in uppercase of every word in that particular class. So we have 2 words, Simple Arithmetic. They are butted next to one another, and it's uppercase S and uppercase A. This is called Simple Arithmetic. The first statement up here is the package statement. This corresponds with this particular package, Simple Arithmetic, all in lowercase. The next is we're going to import this java.swing.jOptionPane class, and that allows us to invoke this method down here, this show message dialog method inside this class. and it's got some parameters. The first parameter is null, and then the second parameter is this calculation with a string included. So here's your import statement, and then the structure is similar to what we discussed. You've got public class simple arithmetic, you've got your opening curly brace, and the beauty behind NetBeans is that it will show you the corresponding closing brace. All I need to do is click to the right of this curly brace, and it shows me that I have a closing curly brace directly underneath this public. Underneath the class is the public static void main method with the string array called args. And I've got an opening curly brace, and here's my associated closing curly brace. This next is a line comment, display the results, and I have in here system.out.println a string incorrect addition, and it goes from there to there. Inside the, I'll get this one here, from there to there. This is going to be treated as a string, whatever you put inside there. Next is a plus sign. The plus sign in Java can mean one of two things. It can mean either addition or it can mean concatenation. Addition, obviously, is to take two values, like 3 and 4, and put them together and come up with 7. Or it could mean concatenation. Concatenation means taking one thing and butting it up directly next to the other thing. So for instance, in here we have a string. Inside the string it says incorrect addition, colon 3 plus 4 equals, and then that's the end of the string. In this particular case, we have a string and a value. And this plus sign needs to be interpreted by the compiler, and it's going to say, I got a string and I got a value. You don't add a string and a value together, you add a value and a value together. So it will therefore consider this as a concatenation sign rather than a plus sign. And that's why when I execute this particular program, you will see, it's going to come out down here, it has incorrect addition. This J-option pane show message dialog box is what just popped up here. I'll move it over here to get it out of the way. But you'll see incorrect addition, 3 plus 4 equals, this is my string, and it used concatenation, and it outputted 34, which is incorrect. The correct addition would be to go ahead and system.out.println and do this character string all the way to here. And then I have my plus sign, and then I put in parentheses 3 plus 4. Now there's an order of precedence in Java. If you put things in parentheses, it will do those first. It will do that operation first. So I put the 3 plus 4 in parentheses. Now the compiler will say I've got a value 3 and I've got a value 4. What do I want to do? Well, values you add. So it will add the 3 and the 4 and come up with 7. And then the next operation is a string and a plus sign and a 7. Well, the compiler says we've got a string and a value. I'm going to concatenate that. So this string will then get concatenated with this particular result, and you're going to get the correct addition is going to be equal to 7, demonstrated down here. Okay, here's some other simple arithmetic. I just do this the string so we can see it, but now I put in parentheses 7 minus 2, and I will get 5 down here. It gets concatenated. Multiplication, good idea when you have multiplication and addition to use parentheses. Whenever there is addition and subtraction, multiplication and division, it will always do multiplication and division first. After it's done with its multiplication and division, it will then do the addition and subtraction. If you have multiple multiplications and divisions, it will go left to right. If it's the same order of precedence, the program will execute left to right. So we have 8 times 5 is going to be 45 right here. That will get, I'm sorry, 8 times 5 is 40. A very important thing down here is integer division. We have integer division, and I'm doing 19 divided by 6. In Java, if you have two integers and they're being divided, you're only going to get integer division, which means 19 divided by 6 is going to be equal to 3. Integer division keeps the quotient and throws the remainder away. And that doesn't seem to be too accurate, because down here we have integer division. 19 divided by 6 is equal to 3. That is incorrect. The precise calculation would need to be identified by putting a decimal point in either the numerator or the denominator, or both. So I've rewritten this statement so that it calculates 19 divided by 6.0. Then Java will say, this needs more precise results, so the 0.0 will then yield the correct answer of 3.1 and 6 repeating. Very important concept here, knowing that this is integer division right here, and this is more precise division. Don't make those mistakes. When you have multiple operations, as I said before, addition and division, use parentheses. The calculations will be done by the order of precedence. Parentheses first, the PEMDAS, if you remember PEMDAS. Parentheses, exponentiation, multiplication, division, addition, and subtraction, in that order. Now, the next statement here is an approximation of pi. This particular character right here, it's embedded within a string, and this is an escape character. This \u is an escape character, and this is a Unicode representation of the Greek letter pi. All the characters on a keyboard around the world in Java are stored in 2 bytes of storage. That includes many wingdings and Greek letters and kanji characters and Arabic letters that we need 2 bytes of storage in order to store all of those associated characters. So this particular expression says this is an escape Unicode character, and it is represented in 4 hexadecimal characters, 03C0. And we'll get more into hexadecimal later on this semester, but that will go ahead and escape out of this string and replace it with the pi symbol, the Greek pi symbol. And what I did was I used 22/7, and I went ahead and used 22.0 divided by 7 in order to get 3.1428. So that is introducing other characters that are not on your keyboard into console output or to a printer or to a terminal. The last statement I just want to introduce to you the power of object-oriented programming. In this particular example, we are, I don't know what happened to my dialog box here. It's somewhere underneath things, but let's just stop that, and I'll run it again so we can generate this. But this dialog box right here is generated by this statement right here, this J-option pane show message dialog. And this is doing nothing more than putting a string out, multiple operations, 2 plus 10 divided by 5 is equal to 2.4. And I had to make sure that I put in the 5.0 so that I got precise division. Otherwise, it would get integer division, and it would be grossly inaccurate. And this plus sign, you can go ahead and span multiple lines. This is a concatenation sign, and we're going to go ahead and do this calculation here, and it gets stored inside this dialog box. All the code for this dialog box is over here in this method, in the J-option pane class, over here in the JavaX.swing library. We'll get more into that later on in the semester, and that's actually going to be an introduction to the next course after the Intro to Programming, the Object-Oriented Programming class using Java. Hopefully you'll take that next semester. So that is simple arithmetic. Let's get back over to the PowerPoint and let's continue on. I'm going to skip over this working in the DOS prompts. The anatomy of a Java program. Okay, obviously this is all the different pieces and the parts of a Java program. We'll talk about the class name, the main method, the statements, the terminator, statement terminators, and reserved words, comments, and blocks. We talked about them a lot already, so I'm not going to spend a lot of time on them. But obviously the class name is the name that comes right after the word class. This is a reserved word, as is public, and this is the class name. Class names start with an uppercase letter. We use simple arithmetic. We used hello world, and they all have uppercase first letters for each word in the class name. The next is the main method. We discussed that. We know it's a method because it has parentheses. Inside the parentheses are parameters. When a parameter gets filled with a particular value, that becomes an argument to that method. And inside this main method is a statement. And the statement, we know it's a statement because it ends in a semicolon. All statements in Java end in semicolons. Right here. Reserved words are public and class, public, static, void. These are all words you cannot use when you decide to create your own class name, such as welcome or simple arithmetic or lab 1 or in class 1 or pre-lab 1 or any of those other classes that we've used so far. You cannot use these reserved words. These are specific and special to the compiler so that it knows exactly how to compile your code. We've discussed this already. Here's your opening curly brace and your closing curly brace for the class block. Right here is the opening curly brace and your corresponding closing curly brace for your method block. Here are the curly braces. They open and close the blocks. Your parentheses, these are used with methods. Your brackets denote an array. So the string with the brackets is a string array that's called args in your main method. We'll talk more about arrays later on in the semester. The 2 forward slashes or double slashes are to denote a line comment. Opening and closing quotation marks are these double quotes, and they are used for strings and the semicolon. I'm going to pause right now just to focus in on these double quotes here. Many keyboard characters for double quotes have sometimes like a different double quote than what we're looking at here. Sometimes you might see a curled double quote, an opening close quote that curls to the right, and another corresponding double quote that curls to the left. If you see that, that's going to be a problem in your NetBeans compiling, because when the NetBeans compiler tries to compile your code, it's not going to recognize those different double quotes. And they're going to look rather similar, almost identical to you. And you're going to wonder, well, why can't I compile my program? And it's because the double quotes that are in your program are not the ones it's expecting. If you're having trouble with that, I would just go ahead and delete the left curly quote and replace it with a single straight up and down double quote. And likewise, the same thing if you have one for a closing quote. Make sure that the quotes that are in your Java program are straight up and down. Otherwise, you will not be able to compile. How does that happen? Usually when you copy code from a PowerPoint or from a Word document or some other document, it will use a different quote in the ASCII character representation that the NetBeans compiler is not going to like. Hopefully I've saved you a lot of headaches and aggravation by focusing in on that. Okay, so here's the example of the closing the curly braces. We don't need to go through that. Here's for parentheses. Here's for semicolon, the forward slashes, and again the double quotes. All right, now I'm going to start focusing in on programming style and documentation. This is as critical, almost as critical as getting your code correct. We're going to look at appropriate comments, naming conventions, proper indentation, spacing of lines, and also block styles. Make sure you use appropriate comments. You can use line comments or you can use block comments. Line comments we know are 2 forward slashes, and block comments start with a forward slash and an asterisk, and will continue on until the compiler sees the corresponding asterisk and a slash. Anything therein is going to be considered a comment. That would be a block comment. When you write a program, you should go ahead and include your name, your class section, instructor, date, and brief description at the beginning of the program. Now, that's what the book tells you to do, and that's what Liang is asking you to do, but I've actually modified that so that you adhere more to industry standards. So I kind of created a program documentation header block for you to use, which has the program name, the program description, the author, the date, and a change control section for the next person that comes in that might have to make a change to your program. So I'd like you to use that in your assignments so that it looks more like it's business-oriented or industry-related. Naming conventions. Choose meaningful and descriptive names. Class names, remember, capitalize the first letter of each word. For example, compute expression, the uppercase C and the uppercase E. Indentation. Indent 2 spaces. And spacing, use a blank line to separate segments of code. Here's one particular example. There's different block styles. The block style that we're going to be using in this class and also in your textbook is the end of line style. This first style, this next line style, where you basically write public class test and skip to the next line and put your curly brace, well, yeah, that does correspond nicely to the closing curly brace, and it also corresponds nicely for the main method, but it spaces your program out unnecessarily so, and it can also cause confusion when you start dealing with nested blocks. So the industry has kind of migrated over to the end of line style, which looks like this, where you have it right at the end of this line, and you open up your curly brace, and you have your corresponding closing curly brace directly underneath the P in public, the modifier for the class. So we're going to stick to that in this class. Please write all your code using this convention. Okay, programming errors. There are syntax errors, runtime errors, and logic errors. Syntax errors are detected by the compiler. I'm sure you've seen plenty of them. As you write your code, you'll see red squigglies, you'll see red balloons, and up in the right-hand corner of your NetBeans, you'll see a red block which says that you have some compile errors. You need to fix those. You cannot submit anything to me that has compile errors on it, or I will take significant points off. You need to fix those. Syntax errors could be a missing semicolon, one too many parentheses, you don't have corresponding left and right parentheses, you have one too many right parentheses, not enough, whatever, or it could be anything else that the compiler is looking for that you've omitted. Runtime errors are cause the program to abort or abend. Abend is another shortening of 2 terms, abnormal ending, and abend is the term that is used in the programming community. That means that you had no syntax errors, but something caused your program to end abnormally. And then the last category is logic errors, and those produce an incorrect result. No syntax errors, it runs fine, but you get the wrong results. That would be a logic error. Here is an example of a syntax error. If we look through this, starting right up at the top, public class shows syntax errors. That looks fine. We've got a closing curly brace, public static. We are missing void. There is no void word in here. So that is going to be a problem. We need to put public static void main. And string is okay with the opening and closing braces, brackets. And then we have system.out.println. We are missing a double quote here. So those would generate syntax errors, and you would need to fix those before you could run your program. Here's an example or an exercise for you to go ahead and do at your convenience. I created a whole bunch of errors inside this program, and you can go ahead and try and identify all the different errors, the syntax errors that I created. One thing, and this should look familiar to you, is your calculation of pi. Make sure you also put 1.0, 1.0, 1.0, 1.0 in order to get precise division. Otherwise, these fractions all will yield integer division, and you will have a grossly inaccurate calculation and result. Here is the solution to that particular exercise. I put all of my corrections in red, so you can check your work. A runtime error would be the result of this particular statement. We've got everything fine here. Public class show runtime errors, public static void main, and we have system.out.println 1 divided by 0. We cannot divide by 0. Can't be done on this planet. Maybe on some other universe they permit it, but right here on the good old Earth, we do not divide by 0. That's going to cause problems, and this will get a runtime error. When you run this and try and divide by 0, you will get an error. You need to fix this somehow. A logic error. Here's where, for instance, if you're converting Celsius to Fahrenheit or vice versa, you could go ahead and accidentally put the parentheses in the wrong spot. I don't think that this is incorrect. I actually think this is correct, but where we get a logic error is we didn't put precise division. We didn't put 9.0 and or 5.0. So this is going to be 9 divided by 5 is going to be 1 in integer division. And we're going to get 1 times 35 plus 32. 1 times 35 is 35 plus 32 is 67. That is an incorrect conversion of Celsius to Fahrenheit. If you put 9.0 divided by 5, well, now you're going to get more precise. It's going to be 1.8 times 35, and I think the result gets up into the 90s. So that would be an example of a logic error. That takes us to the end of Chapter 1. Are there any questions?
I don't have any questions.
Everybody okay?
Yes.
All right. How about the assignments? I gave you 2 in-class assignments, and I gave you 2 labs. In class 1 and in class, I'm sorry, you guys are in the online section, so obviously you don't have in-class, I call them pre-labs. So you have a pre-lab 1 and a pre-lab 1A, and a lab 1 and a lab 1A. For those that are on, do you have any questions that I could answer, or difficulties or misunderstandings about those assignments?
At this point, should we just stick to Chapter 1 in order to finish those assignments, so no declaration of variables on it or things like that?
No declaration of variables. That's a good point. Some people have had programming before, and I'm going to insist that if you have an assignment in Chapter 1, I don't want you to use Chapter 3's skills to solve Chapter 1's problems. You understand?
Okay.
Okay, because, I mean, that's just not fair. I want you to do it using the skills of the current chapter or the previous chapters, but no future chapters.
Okay, perfect.
Okay?
Okay.
Any other questions?
No.
No? Okay,
Well,
everybody go ahead. Who's next?
This is Julio. The other question that I had is, I think it was either one of the pre-labs or lab 1, where the assignment is specifically to use only one print line statement. And so my question is, in future assignments, does it really matter if you need to print out, a series of statements to make it in one, or to do a series of print line statements?
Julio, I'm not aware of me giving an assignment that said you can only use one print line statement.
Well, I think it's a very first pre-lab in which you do your initials, right?
Oh yeah, no, no, actually, I would want you to use multiple print line statements. That
Okay,
would be
well,
like very difficult to do.
well,
Yeah.
because at some point it says, use /n to move to the next line in your print line statement. So I assumed that you wanted us for that particular assignment to use only one print line, which I did, and I think the output comes out correctly. But it was just a question.
Yeah, no, that's a real good question. And for the first couple of assignments, you can use either approach. I didn't want to confuse people with the /n, but if you've been exposed to that, and I think I did briefly describe it, the /n is another escape character that goes to a new line. That gets embedded inside the quotes, the double quotes, so you can go ahead and use a new line symbol inside your quotes, and it will go to the next line. So that's certainly permissible. You can use that.
Okay.
Okay. Any other questions? Anything else, Julio? We also have Mark still on, hopefully?
Yep, I'm good.
All's good? All right, no questions on how the class is going to be run, okay? This is our first webinar, and I hope that you guys understand the routine now. These will be due every week methodically, and I will grade your Lab 1s after the last deadline, which is Lab 1's last deadline was last night, right? It was Wednesday night. So I will get around to the grading. I've got some 70-something labs to grade, so it's going to take me some time to do. But I normally will try and get them done on Thursday or Friday after the Wednesday last deadline. Okay, so I'll try and get to your Lab 1 and grade it. It will be over in your My Grades tab in Blackboard once I've graded it. And I'll usually put a very brief description on things that you may have gotten wrong or suggestions or whatever inside the My Grades tool.
Great.
Okay. If there are no further questions, I guess we can wrap it up for tonight. My intention is to do these for every end of chapter. Chapter 1 was a 2-week chapter because I got a lot of people coming and going, and a lot of people that don't know programming right out of the blocks. But Chapter 2, we're going to go quickly through. That'll only be 1 week. And if I see it necessary, I'll probably do another webinar similar to this one, and we can go ahead and discuss any confusion or uncertainty in that webinar, and that might be, in all likelihood, next Thursday. So I'll send another email out or Blackboard message notifying everybody. Okay, so no other questions? Okay, very good, guys. Okay, thanks for participating. And any questions, shoot me a Blackboard message or just throw it in the discussion tool.
All right, thank you very much.
Have a good one.
Okay, yep, have a good night, guys. Bye. All right, good night.
Have a good night. Bye.
Let's begin by first announcing the webinar disclaimer, as is what I have to do every webinar. This WebEx service includes a feature that allows audio and any documents and other materials exchanged or viewed during the session to be recorded. By joining the session, you automatically consent to such recordings. If you do not consent to the recording, then please do not join or participate in the session. The WebEx service is intended to supplement the classroom experience. Duplication or redistribution of lecture capture recordings is prohibited without appropriate consent. All right, so this is coming in kind of handy due to our snow day today. I do want to get into Chapter 2, since we will just be spending 1 week in Chapter 2, and it is kind of an important chapter. All right, the motivations. In the preceding chapter, you learned how to create, compile, and run Java programs. Starting from this chapter, you'll be learning how to solve practical problems programmatically. Through these problems, you will learn Java primitive data types and related subjects such as variables, constants, data types, operators, expressions, and input and output. Chapter 2 takes on a lot. Okay, the first thing we're going to do is start back from where we started in Chapter 1, and that was computing the area of a circle. This program computes the area of a circle, but it will now use variables as opposed to just calculating an expression in a system.out.println statement. Let's look at the program compute area. I've got a preloaded NetBeans already. See if I can make this a little bit bigger. Okay, we got a package statement for compute area that corresponds to this compute area package. Notice that it's all in lowercase. Packages by convention are in lowercase. The next line says this is the start of a class. The class is called compute area. It's got the proper conventions. It's got the proper casing. We have an uppercase for C and an uppercase for A. Each break in Word should be capitalized, should be in uppercase. So we have compute area in the proper casing. Here's our starting and ending curly braces. Next statement, next line is going to be the declaration of the main method, which starts at the first highlighted curly brace and ends at the second one. And note how they are lined up directly under the P in public for each corresponding one. All right, the first thing we're going to do is we're going to declare some variables. We want to compute the area of a circle, so the variables should be the radius and the area. We are declaring a variable called radius, and it is going to be of the type double. Who just joined? Hi, who just joined? Is this Oscar? I guess, Oscar, we can't hear you. You may need to activate your audio by either calling in via your cell phone, or you can call in via your computer or take yourself off of mute. I see you've just gone to mute, so I'm going to continue. All right, so we're declaring two variables. The first variable is radius. It is going to be of the type, the data type, double. This indicates that it's going to be a numeric data type, a specific numeric data type. And here is a line comment that indicates that this is declaring the radius. The next is declaring the area, and that's going to be a variable. We created this name just called area, and it too is going to be of the type double. Now we're going to assign a value to the radius variable. Assignment statements have an equal sign, and assignment statements go right to left. We will take the value 20, and we're going to assign that over into the radius variable. Now the contents and storage that is named radius contains the value 20. Now we're going to compute. We don't need anything else. We don't need to assign any other variables. We need to compute the area and then assign that into the area in storage called area. All right, so we have radius equal to 20, and we're going to now do this calculation to the right of the assignment operator. This is not an equal sign. This is now referred to as an assignment operator. This variable called radius, which has the value 20 in it, is going to be multiplying this area in storage called radius, which also has a 20 in it. So it's going to be 20 times 20, which is the radius squared, times pi, 3.14159. And that whole evaluation, radius times 3.14159, is going to be calculated and then assigned over into the area in storage called area. Remembering our orders of operation, when you have multiplication, we have two multiplications here. We have the radius times the radius, and we also have the radius times 3.14. So there are two multiplications here. Whenever you have the same level of precedence and multiplication and division have the same level, then the computer will calculate left to right. So it will do this operation first, this multiplication, and multiply the radius times the radius and get 400. And then we have 400 times 3.14159, and that will calculate the overall area. Assign it into the variable called area, and now we do our system.out.println, and we have a literal string right here, and it ends at this blank, and we're going to concatenate this literal string together with this radius, which is 20, and we're going to concatenate another string that has a blank is blank, and we're going to concatenate another variable called area. Let's run this, and we see that the area, make this a little bigger. Well, it's not cooperating. The area for the circle of radius 20 is equal to 1,256.636. Okay, so it did the calculation correctly, and let's just reflect back upon these data types here. These are what are known as primitive data types. And the first one we're introducing you to is the double data type. And the double data type essentially says that the data that's going to be in these two areas in storage is going to have a fraction. It's going to be a large area in storage, and it will contain fractions. And sure enough, as you can see by the result, although this is an integer, it could take 20.1 or 20.2, but we are giving it an integer. It will get evaluated as a decimal, 20.0. And also, the area variable is also of type double, so that means it can handle fractions. And when we did this calculation, and it came out to be 1256.636, that got assigned into the variable called area, which got displayed down here. And it yielded this calculation with the fraction. That's a rather simple program just to compute the area of a circle, and it does demonstrate the introduction of variables. And in this particular case, we are just using one data type. That data type is double. Let's step through a trace of this program. When you declare the radius of type double, well, in storage, memory is allocated for this area in storage. It's annotated as a box over here. There's currently nothing in this particular area in storage. In fact, it's garbage. Okay, it could be a bunch of zeros, a series of zeros and ones, or bits and bits, and there is currently no meaningful value in there. It is garbage. When you declare the next area that happens to be called area of type double, well, it does the same thing. Allocated memory for the area variable, and again, this has garbage inside it as well. Skips over the line comment and goes to radius equals 20, which really means 20 is going to be assigned into the variable called radius. And now we see inside the area in storage, there is a value of 20. Next step, we are going to calculate, we're going to compute the area by multiplying radius times 3.14159. And when that calculation gets completed, it gets assigned into area, and it gets placed in RAM in this area in storage that's been allocated for the variable area. Lastly, we're going to do our system.out.println statement, where we have a string, the area of the circle of radius, blank, concatenated with the radius value, which is 20. Concatenated with blank is blank, concatenated with whatever this evaluation turns out to be. And down here you'll see you get the result, the area for the circle of radius 20.0. Notice it's 20.0 because the radius variable is declared as a double. When the console puts this out, it won't put 20, it'll put 20.0 to let everyone know that this is precise. This isn't integer division that's occurring right now. This is actually precise division, which will include the decimal piece. All right, now next topic is to read input from the console. As people are joining, let's see, we got a few people joining in here, so just please, Joseph, I see you're on. If you could just put your audio on mute, there won't be any distracting background noise. If you have a question, just take yourself off of mute and speak right up. All right, the next slide is to introduce how we can get input from the console. So far, up until now, we've just been putting output to the file. I'm sorry, putting output to the console. Now we're going to go ahead and get input from the console. And the way to do that is you need to create what's known as a scanner object. And the statement that creates a scanner object is this one right here. And you have to make sure that you stick to the proper casing as well. Java is very case sensitive, so you need to identify scanner, which is a class, and we're going to call the object that's going to be created from the scanner class, we're going to call it input. And this equal sign will go ahead and create the object as a new object, and we're going to pass this whatever we put into the console. So that would be your first statement in your program in order to be able to gain any kind of console input. Number two, use the method nextDouble to obtain a double value. If you can think of the example where we're asking for the radius, well, we entered 20 into the program, but you might want to have the capability of your program to enter 20.1 or 20.2. So we're going to ask for a double, or have the capability to accept a double. That would be to utilize this method known as the nextDouble method from the scanner class in order to get input of the type double. And here's an example. We have system.out.print, enter a double value. Okay, so there's no evaluations going on this. All that we're doing is we are sending a literal string to the console. The end user will read that and he'll say, enter a double value. Okay, that I'll put in 20.1 because that is a double value. It's got a fraction. It's got a decimal. The next statement, scanner input, that's where you create. That's this statement up here. You're going to create the object, and it's going to use whatever comes in from the system console. And we will then take the next input dot nextDouble and assign it into a variable called D for double, and it's going to be of the type double. And now you've gotten, if I entered 20.1, now the value 20.1 is in the variable called D in storage in RAM, and it will be of the type double. Let's take a look at a sample program called Compute Area with Console Input. All right, we got a package statement that corresponds with this package folder over here. And we've got an import statement. I introduced import statements to you before for the input dialog box, or the output dialog box, show output dialog box. We now have to go ahead and get another method that we're going to use. It'll be inside the scanner class in this package, the java.util package. So this, whenever you want console input, include the import statement, import java.util.scanner. Next is to go ahead and declare the class. We're going to call it compute area with console input. Notice the casing all the way across. And we're going to have our main method. And we have a line comment. If you could, whoever just joined, if you could just go on mute, it would be great. Thank you. We're going to create a scanner object. Here's our line comment. And this is where we enter this statement, scanner input equals new scanner system.in. Now we ask the question, enter a number for radius, or we request a number. And we want a number that is going to be precise. It's going to be therefore a double, and it will handle any radius, any very large radius, with precision using decimals. The next double method inside the scanner class will go ahead and capture that console input and assign it into this variable called radius that will be of the type double. Then it takes radius, multiplies it times itself, and then multiplies it times this literal value, 3.14159, calculates the whole thing and assigns it into the area variable of the type double, and then we print it out. The area of the circle of radius, whatever I put in, is, and whatever it calculates out to be. Let's do something nice and simple, and I don't know why that's not staying. Come on. Let's put in 20, the area for the circle of radius. I'm trying to make this larger, and it doesn't seem to want to stay. Very annoying. All right, so the area of the circle of radius 20.0, it converted it over to a double, which will now have decimal precision. The area of the circle of radius 20.0 is 1256.636. So it calculated it correctly. I'll do something even simpler, like enter a number for a radius, and I'll put in 10, hit the enter key, and it says the area for the circle of radius 10.0 is 314.159. It's a good idea to test your programs using very simple data that you can quickly see whether or not you're doing your calculations correctly. I know pi is equal to 3.14159, so if I put in a radius of 10, it's going to be 10 times 10, or 100. So I'll move the decimal point over 2, and I'll get 314.159. So I know my calculations are being done accurately. So this is an example of using console input. This next example is called compute average. Let's see what this does. Okay, we've got compute average package, and we are importing the scanner class from the java.util package, and we are declaring a class called compute average, and we've got a main method, and we've got a line comment that will go ahead and there's my, oh, here we go. We have a line comment right here that says create the scanner object. We're going to use the same scanner method, and we're going to assign it into the object variable name called input, and then I can use the next double method on this object from the scanner class to go ahead and get 3 doubles, which will be assigned into number 1, number 2, and number 3, respectively, all of the type double. The next thing that happens is we're going to declare and assign a variable called average, the calculation of those 3 numbers divided by 3, which obviously will work out to be the average. These numbers are all of the type double, so this is not integer division. This has precision in the numerator, so it will yield a precise or a double result, and then get assigned into the variable called average. And the last thing that gets done is to output the result. Running this, I'll enter 3 numbers, and I'll put in 2, 4, and 5. And notice I put them in separated by blanks. And what happens is I'll hit the Enter key now, and you'll see the average of 2.0, 4.0, 5.0 is 3.6s. I put in 2, 4, and 5, and these 3 statements took each of those input values. 2 gets assigned into number 1, 4 gets assigned into number 2, and 5 got assigned into number 3. Then it goes right to left, so it calculates the addition, parentheses is first, so it will calculate the addition of 2, 4, and 5, and 2, 4, and 5 comes up to 11, and then at 11.0, because these are all double types, divided by 3, and we're going to get a result of 3 2/3, essentially, but it's 3.66 repeating. That 3.6s will then get assigned into the variable called average, and then it gets put out to the console. Okay, let's talk a little bit about identifiers. We created some identifiers. The identifiers are average, they are area, radius. These are all identifiers. An identifier is a sequence of characters that consists of letters, digits, underscores, and dollar signs. Now, we only used area and radius and average, so we only used lowercase letters. But you can use these other characters. They are available to you. Here are some of the rules, though. An identifier must start with a letter, an underscore, or a dollar sign. It cannot start with a digit, such as 4 or 2. That is not going to be permitted. The compiler will not like that. Next, an identifier cannot be a reserved word. And you can see the appendix of Java keywords for a list of reserved words. They are things like class and public. Those are all reserved words. So you can't call a variable class. You can't call a variable public. You got to pick something different. An identifier cannot be true or false or null. Those words are used elsewhere, and they too are off limits. And lastly, an identifier can be of any length. It's a good idea to not have them be too long, because you're just going to have to keep typing that in. Personally, I prefer having your identifiers as brief as possible, yet as accurate and concise as possible. Okay, so variables. Compute the first area, and what are we doing here? We're assigning 1.0 into radius, and we're going to multiply now radius times radius. 1 times 1 is 1 times 3.14159, and I'm going to get 3.14159 getting assigned into the variable called area. It doesn't show what type the area is. We're going to assume Above this line somewhere, it's declared area as the type double. And now we're going to print out system.out.println line. The area is, notice this left-leaning brace, or the left-leaning double quote. That could be a problem. This is a PowerPoint presentation, so it's going to do that. And this one looks to be a straight up and down one, so this will not be a problem to the NetBeans compiler. The area is going to be whatever, 3.14 for the radius of 1. The 1 is concatenated. Compute the second area. So this is another segment of code in your program where you assign radius equal to 2.0. This is why they call it a variable, because in this case, it was 1.0. We were using the same area and storage now in our program to assign a different value. It will vary. It's a variable. In this case, radius is going to be 2. It will contain the value 2 in that area and storage. Does the same calculation, and we're going to get a different area. Okay, declaring variables. So far, we've been talking about doubles. The next primitive data type that I'd like to introduce to you is the int data type. And the int data type indicates that anything in this area and storage is going to be an integer. In other words, fractions are not allowed. We're calling this particular integer variable, we're going to call it x. So x is an area and storage. It's going to be of the type int. And here's the line comment that says declare x to be an integer variable. Next is radius of type double. And you can also have another primitive data type called char, which can receive a single character. And in this particular case, this single character, the name in the area and storage is named A. So this area and storage could take any single character. It could take a Q, it could take a K, it could take a parentheses. Any character on the keyboard can be assigned and stored into that area and storage called A. It's of the type char. Assignment statements, well, we kind of introduced that before. This doesn't say x equals 1. This says the value 1 is going to be assigned into the variable called x. You need to make sure that you declare your variables before you do any assignments. You can do them on the same line, but you do have to declare them initially before you can assign things into them. So that assigns 1 into x. This one will assign 1.0 into radius. X is an int type, and radius is a double type, so that's all fine. And we are assigning the uppercase a into the char variable called lowercase a. Declaring and initializing into one step is what I was alluding to before. You can declare and initialize or assign into x all in one statement by doing this. Int x equals 1. That declares x to be of the type int, and we're going to assign 1 into that variable area and storage of type int. Likewise, this is declaring the variable d of type double, and we're going to assign 1.4 into that variable. Named constants. You can go ahead and you can declare a constant in your program, and a constant would be any kind of value that is not going to change for the duration of your program. For as long as your program runs, this particular value or this particular area in storage will not change. A perfect example would be the value pi. Here is the structure. You need to first start off with lowercase final, and then whatever the data type is for this constant, and then you put the constant name in all capital letters. And then you're going to do the assignment operator and whatever that value happens to be. For example, if we wanted to declare a constant called pi, you would write your statement as such. Final, double because it has a fraction, uppercase pi, and we're going to assign 3.14159 for the approximation of pi. Another example might be final int size equals 3. Keeping in mind that this is not a variable, this is a constant. So for the duration, for the life of your program, the area in storage referred to as size will have to not change and always be 3. Naming conventions. Make sure that you choose meaningful and descriptive names. Names like X and Y and Z, they're not very descriptive. And as your programs get more and more complex and people add more code to them, you'll find that you need to have more meaningful variable names. So make sure you use meaningful variable names. You can abbreviate. Most programmers do abbreviate because they're not great typists, and I'm certainly not one. That's a great typist, so I like to abbreviate my variables. I'll type in AVG for average or CTR for counter. Those are kind of conventional abbreviations for those variable names. So make sure you choose meaningful and descriptive names. Next, variables and method names. Use lowercase. That's for both variables and methods. Notice that main is all lowercase. If you create a method, later on you'll be doing that. You'll be creating your own methods. You need to go ahead and use all lowercase characters for their names. If the name consists of several words, concatenate all in one, using lowercase for the first word, and capitalize the first letter of each subsequent word in the name. For example, the variables radius and area are fine, but they're not multiple words. They're all lowercase. And the next example, we have compute area. That would be a method. Usually methods might have an action such as to compute the area. And if you use two words, the two words are concatenated, which means they're butted up next to one another. The first word is in all lowercase, and any other word after that is going to be the first letter in any ensuing words will be in uppercase. So if this was to say compute final area, it would be lowercase compute, uppercase F, lowercase INAL, and then uppercase A, then lowercase REA. That's the convention that you need to stick to. It's for variables and also for method names. Class names. This is review, but you have to make sure that you capitalize the first letter in each word in a class name. The example they use here is compute area. I know this is a class because it has the uppercase C. If it had a lowercase c, I now know it is a method to compute area. But this is a class, so it's going to be uppercase C and uppercase A. Constants, well, you need to capitalize all the letters in constants. And if you have two words, you need to separate them using underscores. The example they use here is pi, which is one word, so that doesn't demonstrate it. But if you have something that says max value, you would declare a constant this way: uppercase max underscore uppercase value. Okay, we've got to describe these primitive data types in a little more in depth. And in order to do that, you have to understand what a byte is. A byte is 8 bits in storage, and a bit can either be a 0 or a 1. It can be on or off, it can be true or false, 0 or 1, clockwise or counterclockwise. It really doesn't matter how you want to think of it. We programmers, we think of it as 0 and 1. But it's binary. It can have only 2 states. And we'll just refer to those states as 0, meaning off, and 1 being on. And each byte has 8 of those. We can go ahead and declare a variable of the type byte right here, and that will go ahead and declare an area in storage that's going to be 1 byte in length, or 8 bits, and these are numeric data types, so it can handle an integer anywhere between -2 to the 7th all the way to 2 to the 7th minus 1. In parentheses, it gives examples. So in a byte data type, you can store any numeric integer between -128 and +127. If it's larger than that, such as -129 or +128, you now need to go to the next larger data type, which would be short. And short is actually 2 bytes, or 16 bits. It's a 16-bit, and it's signed. The first bit indicates whether it is positive or negative, and the remaining bits actually have the magnitude of the number. So this short data type can handle any integer between -32,000 all the way up to +32,767. Those aren't used too frequently. What are used more often than not are integers, or int, and doubles. Integers, an int data type, can handle any integer from -2 to the 31st all the way up to +2 to the 31st minus 1, or the actual values are in parentheses. An int is a 4-byte area in storage, or a 32-bit signed area in storage. The first bit is a signed bit, and the next 31 bits is going to be the actual magnitude of that number. After int comes long. We're just working now with integers. So this is now a long numeric data type, which can handle extremely large integers. -2 to the 63rd all the way up to 2 to the 63rd minus 1, or these values here. So that's very, very large integers. It's actually a 64-bit or 8-byte area in storage. Next is a float. Now we're talking about decimals. And decimal numbers can be stored in 2 different data types. The first one is called a float, and a float can have this range in it, and it's referenced in scientific notation. So this is -3, and this e is 10 to the 38th, all the way up to, this is now in very large numbers here, but it is a 32-bit float number. In other words, it's a 4-byte area in storage that can handle fractions, decimal places. If you need a larger area in storage, or a lot more precision, then you would then go to the double data type, which we've been working with all along. And that negative range is from here all the way up to the positive range here. And it is a 64-bit or 8-byte area in storage. So that's pretty much the different data types for numeric data. Again, we will be pretty much using ints for integers, because this range here seems to cover everything that we would need, and doubles for any kind of decimal numbers, because this range certainly covers that area in storage. These 2 here are known as floating point numbers because there's a point, there's a decimal point, and not to be confused with a floating point, which is a 4-byte floating point number, and a double floating point number, which is an 8-byte, much more precise area and storage data type. Okay, reading numbers from the keyboard. We showed you before how you can bring in a next double, and I could enter 20.1. Well, if I only want integers to be entered, then you might want to go ahead and refer to things using int values. Here we're going ahead and declaring the input object of the type scanner, just as in the example before. And now I know I'm getting an integer from the console, so I'm not going to use input.nextDouble, I'm going to use input.nextInt, open and close parentheses, and it will get from the console the next integer and assign it into the value, the variable called value. It will be of the type int. And here are some other methods that you can use to retrieve from the console all the different data types. If you needed to retrieve a number less than 127, from 0 to 127, you could use byte, and you could use the next byte method to retrieve that. Next short would be for 2 bytes integers. Int would be 4 byte integers. Long as 8 byte integers. Next float for 4 byte decimals, and next double for 8 byte doubles. These are all methods that are available to you. Let's look at some numeric operators. The first one is the plus sign. The plus sign for numeric operators means an addition, keeping in mind that it also can be interpreted as a concatenation sign. And a concatenation sign is when you want to butt 2 things up next to one another. In this particular case, I want to add 2 values, 34 plus 1. The compiler will go ahead and say, here are 2 values, 34 and 1, with a plus sign in between. Therefore, a value probably wants to be added to another value. And that would go ahead and yield a result of 35, not 341, which would be the concatenation sign. Next is a subtraction sign. That is rather obvious, so you can use these operators, 34.0 minus 0.1, and you're going to get 33.9, assuming that these, if they're variables, they are of the type double. Multiplication is the asterisk sign, / for integer division, and you can go ahead and make it precise now if you put in the division operator a 0.0 or a 0.0 in either the numerator or denominator or both, and you'll get precise. It will be of the type double, floating point, if you put in the decimal point in there. The next one is an interesting one. It's called a modulus function or a remainder function. And as with integer division, where if I did 4 divided by 3 in integer division, the result is going to be 1. It takes the quotient and throws away the remainder. Let's go with a better example. Let's say 7 divided by 3. The result in integer division would be 2, not 2.3. The fractional piece gets thrown away in integer division, and the quotient is the only thing that gets returned. If you want to get the fraction piece, you can use this percent sign or this modulus operator, and that will return the remainder and throw away the quotient. The example given here is 20 modulus 3. So that is going, the real division is going to be, what is that, 8, it's going to be 6 and 2/3, right? Well, it throws the 6 away and just returns the 2, just returns the remaining piece. So it's 6 with a remainder of 2, it throws the 6 away, and it will return the 2. This does come in handy. We'll go through some examples later on, but this does come in very handy when we're doing our calculations. Here are some examples of integer division. 5 divided by 2 yields an integer 2 because we're dealing with integer division. 5.0 divided by 2 will yield a 2.5 because now we've asked it to be more precise, and it will go ahead and convert these values into doubles, do the calculation, and return back 2.5. 5 modulus 2 will yield a 1, the remainder of whatever the division is. Here's an example. Remainder is very useful in programming. For example, an even number modulus 2 is always 0. And an odd number modulus 2 is always 1. So you can use this property to determine whether a number is even or odd. Suppose today is Saturday and you and your friends are going to meet in 10 days. What day is 10 days from now? You can find that day is Tuesday using the following expression. We have, today is Saturday. Saturday is the 6th day of the week. So if we're going to add 10 days, we can reference Saturday as day 6 plus 10. That's going to be 16, and there are 7 days in a week, so we're going to do with a modulus 7, and that will basically break it up into weeks, and we're going to have a remainder of 2. And 2 would be the 2nd day in the week, so that's our remainder. So after 10 days, the 2nd day in the week is Tuesday. Monday is the 1st, Tuesday is the 2nd, and Saturday is the 6th, and Sunday is the 7th. So that is one way in which you could go ahead and write a program or a small little statement here to determine what particular day it will be 150 days from today. You can go ahead and do it that way using the modulus function. Okay, displaying time. Write a program that obtains minutes and remaining seconds from seconds. We'll look at display time. We've got our package statement. We've got our import to get console input. And we will now write a class called display time. We only have a main method in here. And the first thing we do is we create the object called input from the scanner class. And now we can go ahead and ask the end user to enter an integer for seconds. We don't want fractional seconds. We want integer seconds. We will then use the nextInt method from the scanner class and assign whatever I put in into the variable called seconds. And it will be of the type int. Next thing I do is I do integer division, right? Because seconds is coming in as an integer. It's being stored in an area in storage that is of the type int. And we're going to go ahead and divide by an integer. Therefore, we're going to get an integer. We're going to get the quotient in return, and the fractional part will get removed. It will be ignored. Next, we declare a variable called remaining seconds. And the remaining seconds is going to use the modulus operator. And we're going to take seconds, whatever I put in, modulus 60, and it will return the remaining seconds that are part of the remainder. Then we print out, system.out.println, whatever number of seconds I put in. Let's say it was 122. Let's run this so we can do this. We'll run this, and it's going to ask me, if I can make that bigger, it still won't stay. All right, an integer for seconds, I will put 122. We know that's going to be 2 minutes and 2 seconds. Enter that, and it says 122 seconds is 2 minutes and 2 seconds. So it calculates correctly. And the way it does it is by this statement right here. System.out.println, seconds, which happens to be 122, that's what I put in, and we stored it into the area in storage called seconds. 122 concatenated with the literal string, seconds, is concatenated with minutes. Well, that's what I stored using the integer division, sorry. So that's 2 concatenated with this literal string here, minutes and blank, and now we're going to concatenate finally the remaining seconds. And the remaining seconds is in this variable here of the type int, and it's going to be whatever the calculation of seconds modulus 60. That would be 122 modulus 60. That would be 2 and 2 seconds. It throws the 2 minutes away and keeps the 2 seconds and stores that in remaining seconds. And then you just follow up with the remaining literal, and that's where we get this output here. So there's a pretty good example of using the modulus function to solve a particular problem. Okay, note, calculations involving floating point numbers are approximated because these numbers are not stored with complete accuracy. For example, we're using doubles now. And if you look at the system.out.println and we take 1.0 minus 0.1, minus 0.1, minus 0.1, minus 0.1, minus 0.1. We have 5 minus 0.1s, right? So 1.0 should yield a 0.5 when you do this calculation. You're taking 1/10, 5/10 away from 1, and it actually displays 0.5 and a whole bunch of zeros and a 1 at the very end. It does not display 0.5 exactly. And that is because floating point numbers are approximations. So you could be off by 1 bazillionth, if whatever that decimal happens to be. Another example, system.out.println, 1.0 minus 0.9 should yield 0.1. But if you run it in your program, it will display 0.099999998. Very close to 0.1, but not exact. Integers are stored precisely, though. So floating point numbers are approximations, and integers are stored precisely. Calculations with integers yield a precise integer result. Here's another example of using some methods at our disposal. Inside one of the system packages, there is a math class which has many methods inside it that you can use. And inside the method is a calculation that saves us from having to do what oftentimes are normal calculations. For instance, the first example is system.out.println, and I am calling the POW method in the math class, and I'm taking 2 and raising it to a power of 3. And running this program, it will display 8.0. 2 to the third is 8.0. The POW method will use doubles, so you can actually raise 2.1 comma 3, and that will raise 2.1 to the third power. So it needs to use, it'll calculate things in doubles. We know that this is a method because it has parentheses and parameters are separated by commas. So this POW method is getting 2 parameters. The first parameter is 2, then we have a comma, and then we have a second parameter, which is 3. Once those parameters are evaluated to 2 and 3, they then become arguments to the POW method inside the math class, and it will calculate 8.0. Another example is math.pow for raised to the 0.5, which will go ahead and take the square root of 4, and you will then get 2.0. Next is math.pow 2.5 raised to the second power, and you're going to get 6.25, 2.5 squared. This next one uses negative numbers, which is this is the exponent, this is the base, this is the exponent. So now what we have is we have 1 over 2.5 squared, and we're going to get this fraction, 0.16. And then last but not least, there is an absolute method called ABS in the math class, where if I was to subtract 4.5 minus 5, well, that should be minus 5, but the absolute value method, the ABS method, will go ahead and return back the positive result, which is the absolute value. So 4.5 minus 5 with the absolute value will return a positive 0.5. Number literals. A literal is a constant value that appears directly in the program. For example, 34, 1 million, 5.0 are literals in the following statements. We will use the term literal to say we're going to assign the literal 34 into the int variable I. We're going to assign the literal value 1 million into the long variable called x, and we're going to assign the literal value of 5.0 into the variable d of the type double. Integer literals can be assigned to an integer variable as long as it can fit into the variable. A compilation error would occur if a literal were too large for the variable to hold. For example, in the statement byte b equals 1,000 would cause a compilation error because 1,000 cannot be stored in a variable of the type byte. The largest is 127 or negative 128. Anything beyond that range, on the outside of that range, is going to be an overflow. It will not work, and you're going to get a compile error. An integer literal is assumed to be of the int type whose value is between this and that. To denote an integer literal of the long type, you can append it with the letter L, or this is a lowercase l. I don't recommend you use the lowercase l because that gets oftentimes confused with the number 1. Floating point literals are written with a decimal point. By default, the floating point literal is treated as a double type value. For example, 5.0 is considered a double value. Way back when we were calculating pi in our first assignments, and we had to put 1.0s into our numerators, it turned into doubles by doing that. Not a float. Remember, doubles are 8 bytes and floats are 4 bytes. You can make a number a float by appending the letter lowercase f or uppercase f, and make a number a double by appending a lowercase d or uppercase d. For example, you can use 100.2f to denote or 100.2 uppercase f to denote a float data type, and likewise adding the d's will denote a double number. A double versus float. Again, they are both of the type. They're both floating point numbers. Double is twice as large as float, and if you want to take a closer look at them, the double type value are more accurate than the float type. And then, for example, we use this, and we say 1.0 divided by 3.0 is, that's all a string, that's a character string. And we're going to concatenate 1.0 divided by 3.0 is going to display this large amount. This is 16 digits because it's going to be of the type double. However, if we went ahead and specified that it be of the type float by using this approach and putting an F at the end of each of these, you're going to see that it's only going to carry 7 digits. And it will kind of round on that 7th digit. But that is going to be of the float data type. Up here is the double data type. Scientific notation, floating point literals can also be specified in scientific notation. For example, 1.23456 E plus 2 is the same as writing 1.23456 E2, which is equivalent to 123.456, and 1.23456 e to the minus 2 is equivalent to moving the 2 decimal point over 2 to the left. E, or lowercase e, represents an exponent and can be either in lowercase or uppercase. So that was scientific notation. It would be the exponent of your base 10. Arithmetic expressions. If you're giving a math problem that looks like this from your math class, well, you need to go ahead and convert that over into Java code. And we now know that you'd have to go ahead and take this and divide it by 5 and then subtract this big long fraction, which is all of this calculation. Remember that parentheses are done first. Next are multiplication and division. And then last but not least are addition and subtraction. So you have your orders of operation, your PEMDAS, parentheses, exponentiation, multiplication, division, addition, subtraction. And then last is the last fraction here. And you would have to calculate that in the right order. To translate that over into Java code, you need to go ahead and express it in this fashion. And I'll let you look at that a little closer, but this is how you would go ahead and express this mathematical expression up top. Though Java has its own way to evaluate an expression behind the scene, the result of Java expression and its corresponding arithmetic expressions are the same. Therefore, you can safely apply the arithmetic rule for evaluating a Java expression. So we know that parentheses are done first, then exponentiation, multiplication, division, addition, and subtraction. In this long expression, we've got an addition, a multiplication, an addition, a multiplication, parentheses, and a subtraction. Well, the first thing the Java compiler will do is do the parentheses. It then will evaluate this to be 7, and now we have a 7 down here. We've got an addition, a multiplication, an addition, a multiplication, and a subtraction. It does multiplication next. There are no more parentheses. It does multiplication and division. It will scan left to right. Oh, I hit a multiplication. I got another multiplication over here, but I'm going to go left to right. So I'll do this 4 times 4, and that will yield a 16. So now I have an addition, a multiplication, and a subtraction. The compiler will do the multiplication. 5 times 7 is 35. Now, the next iteration, I have an addition, and a subtraction. The compiler says addition and subtraction, they're of the same level of precedence. It will go left to right. It evaluates 3 plus 16 and comes up with 19. Now I've got an addition and subtraction, same level. It will do addition. 19 plus 35 is 54, and then it only has one more operation, and it will go ahead and subtract 1 from 54, getting a result of 53. That's how the orders of operations work. Hopefully that helps you out in creating your expressions, your arithmetic expressions. Okay, last slide. This is going to be reminiscent of your last assignment, which is to write a program that converts a Fahrenheit degree expression over to a Celsius expression using this formula. Celsius is equal to 5/9 times the quantity, Fahrenheit minus 32. We have parentheses, we do them first. We have a parentheses here and parentheses here, so we go ahead and do left to right. We'll do this parentheses first. In Java, you need to write 5.0, otherwise you're going to get 5 divided by 9, which is 0 in integer division. We want 5.0, so that will be done first. Then this will be done second, and then the last thing that will be done is the multiplication of the remaining 2 results. Let's look at the program, Fahrenheit to Celsius. Okay, we got our package statement. We have our import statement for the scanner. We're going to go ahead and create the object called input, and we're going to then use input.nextDouble to store some degrees in Fahrenheit that we're going to ask be entered into the console. The next thing that happens is it takes the value Fahrenheit, which is of type double, and replaces that in here with this expression, and it will calculate that and calculate this, and then the next thing, and store it into this variable called Celsius. It will be of the type double, and now we just put the output, Fahrenheit, and whatever I put in is whatever the Celsius calculation is in Celsius. Running this, I can go ahead and enter a degree in Fahrenheit. I don't know, Fahrenheit, it was pretty cold today. Let's say 27 degrees today. Well, 27 degrees in Fahrenheit is minus 2.7 in Celsius. Running it again. If it's a real hot day of 95 degrees, well, Fahrenheit 95.0 is 35 degrees in Celsius. Okay, so that is orders of operation using variables and the levels of precedent. I do want to stop right there. This is a good breaking point right here. And just go over your in-class assignment, which is just an exercise in what we've just been discussing. Your in-class assignment or in-class 02, for those of you that are in the online class, this would be your pre-lab 2. It's essentially the same exercise. What I'd like you to do is write a Java program that prompts the user to enter a radius and height for 2 different size cylinders. The formula for the volume of a cylinder is volume is equal to pi times radius squared times the height. Declare a constant called pi and initialize it to 3.14159. So we're going to have 2 cylinders, presumably a smaller cylinder and a larger cylinder. I'd like you to declare all variables as type double. The program will calculate the volume of each cylinder and then the difference between the 2 cylinders, the 2 volumes. The program will output the results in the following format. Note that the difference is expressed as a positive number. You can use the math.absolute value method that I just talked about back in slide whatever to determine the absolute value of the result. For example, if you have 2 volume variables, volume 1 and volume 2, well, you don't know which one is bigger, so you can use the absolute value method to just say, let's just subtract volume 2 from volume 1. If it happens to be negative, if volume 2 is bigger than volume 1, it'll be negative, but the absolute value method will go ahead and return the positive value. Be sure to use a program header block similar to the one below, and you can just copy and paste this and change the program author to be your name and whatever date you worked on it, and just the description I think is fine. Here are some sample runs that I did for when I wrote this program. We're going to get scanner input. It's going to ask the question, enter radius and height of the first cylinder. I put 1 and 2. The volume of the first cylinder is 6.28318. Enter the radius and height of the second cylinder. I put 2 for the second radius and 3 for the height of the second one. It calculates and says the volume of the second cylinder is 37.69, etc. The difference in the volumes is 31.4 whatever. I ran it again, and in this case, I gave it not integer input, but I wanted to make sure that double input worked. So the first radius I put as 1.6, and the height is 3. It calculates it, and the second cylinder has a radius of 4 and a height of 8.13. And it calculated its volume, and then I subtracted the 2 And I use the absolute value method to determine that the difference between the two volumes is 384.5 units, whatever it may be. Please send your zip project file as an attachment in Blackboard message for class attendance credit. Another note is you do not need to create two scanner objects. You can repeat or you can reuse the object and just get new input from the console and still use the same input object. You don't need to do that twice. Okay, that takes us to the end of this webinar. Does anybody have any questions at this point? We have Eric, Joseph, Malik, Oscar, Sharon, and that's it. Everybody okay? Everybody good? Okay, if I'm not hearing anything, I'm assuming that there are no questions, so we will call this the end of the webinar, and hopefully the weather will cooperate on Wednesday, and we can meet. And any of you guys online, please send me messages or use the discussion tool if you have any questions. Thank you guys for participating, and we will talk again soon. Take care.
Okay, Professor, mine's just been sent, been zipped.
Okay, great. Thank you, Michael. Okay, as with all webinars, I must go through this webinar disclaimer. So this WebEx service includes a feature that allows audio and any documents and other materials exchanged or viewed during the session to be recorded. By joining the session, you automatically consent to such recordings. If you do not consent to the recording, please do not join or participate in the session. This WebEx service is intended to supplement the classroom experience. Duplication or redistribution of lecture capture recordings is prohibited without appropriate consent. All right, now extending or indexing all the way to slide 36, because that's where we're going to pick up from the first lecture in Chapter 2. It is currently right here. And what it does is it starts off with a problem, and the problem says to display the current time. Write a program that displays current time in GMT, or Greenwich Mean Time, in the following format, where you have the hour, colon, minute, colon, second, such as 1:45 and 19 seconds. So that would be 1:45 a.m. in the morning and 19 seconds. Well, in your computer and in Java, you have the capability of capturing the number of milliseconds since 1970. There is a method called current time millis in the system class that returns the current time in milliseconds since midnight, January 1, 1970, Greenwich Mean Time. 1970 was the year when the Unix operating system was formally introduced. You can use this method to obtain current time and then compute the current second, minute, and hour as follows. Here's a little diagram down here. This is called the Unix epoch, which is the beginning of time, or the beginning of Unix time, which started January 1st, 1970. And since that point in time, our computers have been capturing the number of milliseconds since 1970. That's quite a large amount of milliseconds. There are 1,000 milliseconds in 1 second. So that's going to be a very large number. All right, now how do we do this? Well, the first thing you might want to think about is creating an algorithm. This gets complicated, so what your approach should be to break this problem down into parts, into steps. That's what an algorithm is all about. The first thing that you may want to do is to obtain the total milliseconds since January 1st, 1970. And we'll store that into a variable called total milliseconds. That's a good variable name. It conforms to our conventions, which variable name should have a lowercase for the first word, and any ensuing words thereafter should be uppercase on the first letter. So total milliseconds is properly named by our conventions. So we'll store that very large amount of milliseconds in total milliseconds by invoking the system.currentTimeMillis, and we're going to use an open parentheses and a closed parentheses. That tells us that it is a method. A method is nothing more than a little program that does work for us. And in this case, it will go off and get the number of milliseconds that's stored in our computer. Essentially what that does, it will go to the CPU, and the CPU, inside the CPU, there is the system clock. And the system's clock keeps time using milliseconds. And it does so by the Unix epoch since 1970. So this method, currentTimeMillis, will return back the exact number of milliseconds at that particular snapshot in time. Whenever they developed this slide, it looked like it might have been, for instance, a number of that magnitude, a very large integer of milliseconds. So that's the first thing you do. You get the number of milliseconds. The second step is to obtain the total seconds. We'll store it in a variable called total seconds, another good name for using our naming conventions, by dividing the total milliseconds by 1,000. After all, this is the total number of milliseconds. Divide by 1,000, and you're going to get the number of seconds. So this big number divided by 1,000, this is integer division, so it does not capture the remainder, and you're going to get that number of seconds since 1970. The next step in our processing, as we think this through, is to compute the current second from the total seconds. So we'll do a modulus function or a remainder function on the total number of seconds. Here's our total number of seconds, and we do a modulus or remainder function, and we'll get 8. That's the remainder after doing a modulus 60. That's the remaining seconds, and it will throw the quotient away. That's going to capture the current second. The fourth step is to obtain the total minutes. We'll use a variable named total minutes. We'll divide total seconds by 60, and that will give us the total number of minutes. And that's the number of minutes since 1970. The fifth step is to compute the current minute from total minutes. We'll do a modulus 60 on the total minutes, and that will tell us that we are now currently in the 31st minute of our hour. So this is the current minute. The sixth step is to obtain the total hours by dividing total minutes by 60. And here we do that. We have the total minutes, and we're doing integer division by 60, and these are the total number of hours that have elapsed since 1970. The final step is to compute the current hour from the total hours by doing a modulus 24, and that will get us the hour into our day. So the total number of hours, modulus 74, brings us to the 17th hour in the current day. So that's algorithm development on what looks to be a rather complicated problem, obtaining the current time using the milliseconds. Now you would take this algorithm and start writing the Java code for this, step by step by step. Let's go over to this program here called Show Current Time. Okay, here's our program, and I will run it so we can see how it works. And it currently produces a time of 1:08 48, and that's Greenwich Mean Time. Now it's 8 o'clock. It's a little after 8 o'clock, like 8:08 and 48 seconds here in Connecticut. But over there in England, it's 5 hours ahead of us, and 5 hours ahead would be 1 o'clock in the morning, 1:08 and 48 seconds. So it calculates correctly. Let's look and see what it does. Essentially, we're getting the system, we're going to the system class, and we're getting the current time in milliseconds. And we know it's a method because it has parentheses. See if I can make this a little larger. And inside parentheses for methods, that's where the parameters are located. In this case, we have no parameters. Parameters are separated by commas, and there is nothing inside the parentheses. So this particular method, called current time millis, does not require any input. It doesn't require any additional parameters for it to work upon. If a parameter gets evaluated and a certain value gets placed in a parameter, that's called an argument. So it gets no arguments, it gets no parameters, because it knows what it needs to do. The current time millis method will go to the system clock inside the CPU. In there is where the current milliseconds are, and it will return whatever large number that is and store it into this variable called total milliseconds. Total milliseconds is of the data type long. If everybody could put themselves on mute, it would be appreciated. So the total milliseconds is a variable of type long, which means it's an 8-byte area in storage. It's a very large area in storage, or 64 bits. And it is of the type long, so it's going to be storing a large integer. There's enough room for the current time in milliseconds to be stored there. Although, from what I read, maybe in a decade or so, or two, we will run out of space in a long for all the milliseconds stored since 1970, and then we're going to have to come up with a different way to capture time. But for now, we should be good for a few more years. All right, total milliseconds is stored. Next step is going to be to take the total milliseconds and do an integer division of 1,000. And that will store the total seconds. In this variable called total seconds, it too is of the type long. The next step in the algorithm is to go ahead and take total seconds that we just captured and do a modulus 60 on it, or an integer, or a remainder 60 function, and store that into a variable called current second, also of the type long. Notice there are line comments for each one of these steps because this program is a little bit more complicated than what we've done in the past. So line comments do come in handy so we can see what we're doing. The next step is to obtain the total minutes. How do we do that? Well, we go ahead and we get the total seconds and do integer division by 60, store the results of that in total minutes of the type long. Next step in our algorithm is to compute the current minute in the hour. Well, if we go ahead and take the total minutes and do a modulus 60, we're going to get the remainder minute, whatever that might be. In this case, it was 8 down here, and we're going to store that in current minute of the type long. Then we store the total hours by dividing the total minutes by 60, storing that in total hours, and then we're going to take total hours and do a modulus 24 to get the current hour. Finally, the last thing that gets done, I've got some commented out code here we'll get to shortly. But here's where we print out the current time is, and we have concatenated with that string, current time is, we have concatenated the current hour concatenated with a colon sign, concatenated with the current minute, concatenated with another colon sign, concatenated with the current second, concatenated with the string blank GMT for Greenwich Mean Time. And if I run it one more time, you'll see that it is now 1 a.m., 14 minutes and 17 seconds over in England. What I did down below is to just demonstrate that if you had a customer and they asked for you to print out the current time and you produce this, in all likelihood, that customer here in Norwalk is going to say, that's great, but I don't want Greenwich time, I want Norwalk time. Well, that would be a change that that customer would want to have done with your computer program. Up here is where we get to demonstrate and utilize our program documentation header block, where the change process takes place. You would sit with your customer and say, okay, you now want to introduce a change into this current time program, and we'll call this change number 1. I'll log it in, and I'll put the current date in here, and I would be the program author, or the one who is owning the change to this particular change, and then the brief description. Reflect AM and PM and also Eastern Standard Time. The customer, upon thinking upon it, said, you know what, I'm not very good with this military time, because if it was 11 o'clock, it would be 23, the hour 23. And our customer wants that to be changed to 11 p.m. All right, so where would I go ahead and do that? The first thing I do is enter the change control information, and then down below I would use, and using line comments, the change number. So I now know that this section down here is where I added for change number 1. I'll look down here for a second first. And in Chapter 3, it's going to introduce to you selection statements, which are if statements. If, then, else, if, that type of thing. Well, what we need to do is first use this kind of logic to say if the current hour minus 5, because we are now subtracting 5 from Greenwich Mean Time to get Eastern Standard Time, if we're subtracting 5, and if it's greater than 12, we want to go ahead and subtract 5 and 12 and put PM at the end. If it's not the case, else, if the current hour minus 5, which is Norwalk time, is equal to 12, that would be like noon time, at noon and 5 minutes and 3 seconds, for instance, then you would print it out with the current 12, followed by the minute, followed by the second, and then PM as well. And then else, the final condition, that would be where you would just leave it alone and reflect AM. Now, you might want to test this with different criteria. For testing purposes, I put a comment in here where I hard code in a particular hour. Rather than go through that using the system milliseconds, I'm going to just introduce a literal value, the 16th hour, and directly assign it into current hour. So let's uncomment this to test it. And then I can also take this code, which is currently commented out, and I'll come up here to the uncomment icon, and that will remove the comments. And now I can run this using the 16th hour. And it says the current time is 16:18 Greenwich Mean Time. However, the current time in Norwalk is 11:18:42 Eastern Standard Time, AM. So that looks like it handles the morning hours. Let's now change it to be 17, which would be 5 o'clock over in 5 p.m. over in England. I'm sorry, it is with 17. It is over there. It would be 5 p.m. and over here it would be 5 minus 5, and this is where we're testing the noon hour, and this is where it in effect does show that it reflects 12:19 and 9 seconds p.m. as opposed to 0:19 minutes and 9 seconds p.m. I want to reflect that it says 12. So that's what this code in here is doing. So it handles 17. It'll handle 18. Running that. And now it's reflecting 1:20 and 8 seconds in the afternoon. So it looks as though my code is working pretty good. Let's also look at hour 23 at 11 p.m. in England. Oops, I didn't do that, did I? 23. If I run that now, it looks as though it's handling 6 p.m. It's 11 p.m. in England, and it's 6 p.m. in Norwalk. So it's looking like it's handling my change. I reintroduce that. I show that to my customer. My customer says it looks pretty good. And then within a few hours, all of a sudden, it blows up. Because if it's 1 a.m. in England, once it becomes 1 a.m., look at my code. I run this. It's currently 1:21 and 20 seconds GMT. In Norwalk, it's coming out as -4 a.m. That's incorrect. So I overlooked something in my testing. I thought I covered all my scenarios using the different hours by hard coding it in here, by putting literals in rather than calculating the milliseconds. So I now need to introduce a fix. And the fix would be to fix when Greenwich Mean Time is less than or equal to 5. Because once you get after midnight in England, you subtract 5, you really should be going back into the previous day in the evening, in the late evening. I didn't put this code in here, but I just wanted to demonstrate to you how the change process works. You first delivered your solution, which used Greenwich Mean Time. The customer said, I need Norwalk time. You introduced Norwalk time, but you did overlook when it's after midnight in England, all the way up until 5 a.m. in England, you're going to get incorrect times. So we would need to go ahead and create yet another change to this program. Okay, so that's an example, a real-world example of introducing a change into an existing program and then applying a fix to it. Okay, these augmented assignment operators, these are just other ways in which you can do your coding. This particular first one is a plus equals. This is an operator, a plus equals, and it's a combination of two things. This essentially is saying this is an addition assignment. So if you ever saw code, or you chose to write code that looked like I plus equals 8, this is the equivalent of saying I equals I plus 8. In other words, this is an assignment statement, and you are evaluating this right-hand side of the assignment statement first. If I has 3 in it, well, we're going to take whatever's in I, which is 3, we're going to add 8 to it, we'll get 11, and then we will take the value 11 and store it back into the variable called I. Wherever that location is in storage, that will now have an 11 in it. You can write the code in this format. It's nothing more than a shortcut or a quick way to write I equals I plus 8. You can write it as I plus equals 8. And you can interpret it as I equals I plus 8. Likewise, there's a minus equals, which is a subtraction assignment. And here we have I minus equals 8 is going to be the same thing as I equals I minus 8. And that says whatever's in I, let's assume it's 3, we're going to subtract 8. We're going to get -5, and we're going to store -5 into the variable I. The next is multiplication. They all work the same. I asterisk equals 8 is the same as I equals I times 8. So we're going to take 3 times 8, make it 24, and I now will contain 24. The division assignment, I slash equals 8, is going to be equal to I equals I divided by 8. This is integer division. We're going to have I equals 3. 3 divided by 8 in integer division is 0 because we keep the quotient and throw away the remainder, and the quotient is 0, and the remainder is 3, but we throw that away. So 0 will now get assigned into the variable I. The last one is the modulus function, the remainder assignment. I modulus equals 8 is going to be equal to I equals I modulus 8. 3 modulus 8 is going to return a remainder of 3, and 3 now gets assigned into the variable I. Those are augmented assignment operators. They're used quite frequently. Next is the increment and decrement operators. You will see code, or you can write code, in this format. We have the operator. Let's say we have a variable called var. If you do a plus plus on var, that is a pre-increment. The plus signs are in front of the variable name. The description says the increment var by 1 and use the new var value in the statement. What does that mean? Let's go through an example. Let's assume that I is equal to 1. We're declaring a new variable j. It's going to be of the type int. And what are we doing? We're going to go ahead and we're going to pre-increment I. Increment means to add 1 to it. So we're going to pre-increment I. I currently is 1, so we're going to make that now 2. Because it's a pre-increment, we do that first, and then we assign the value 2 into j. So j is 2, and I will also be 2. The next operator is var plus plus. That's a post-increment, because the plus signs are after the variable name. Let's go through this example. We assume I is equal to 1. We're declaring a new variable j, and j is going to receive the results of this. I is 1, and we're going to do a post-decrement. So the first thing it does is it takes j, and that's 1, and assigns that into the variable j. And then I gets incremented by 1, and now I becomes 2. So after this statement, j will contain a 1, and I will contain a 2. Over here is a pre-decrement. We're doing a minus sign, and a minus sign in front of the var variable. That says decrease the value by 1. That's a decrement. The example, assuming I is equal to 1, we're declaring j, and we are pre-decrementing I. So the first thing we do is subtract 1 from I. Now I will contain 0, and we're going to assign 0 into j. They will both contain 0, both j and I. Here is a post-decrement on the variable var, and the example that they give is Assuming I equals 1, we are going to do a post decrement on I. So the first thing that we do is take I, which is 1, assign it into J, and then we do the post decrement. I will then become 0. After this statement, J will contain a 1, and I will contain 0. That's how these increment and decrement operators work. The pre-increment, post, pre-decrement, and post. Here's an example that you may want to step through. Let's say that I is equal to 10. We have a new number called new num. It's going to be of type int, and it's going to be assigned the results of this, 10 times I plus plus. Okay, well, if I is 10 and it's a post increment, I is 10, and we're going to multiply that by 10. So we're going to now have new num equal to 100. And then I is going to get incremented to 11. So new num will have 100, and I will have 11. It's the same effect as if we did this. Here's another one where we have I equals 10, and we are declaring a new variable called new num, and this is going to do a pre-increment on I. So we'll multiply 10 times the pre-increment, so I is now going to be 11, and we're going to multiply 10 times 11 and store 110 into new num, and I will contain 11 because it has been pre-incremented to 11. All right, so that's code that you may see, you may choose to use. It's rather used just to shortcut things. Frankly, I'm more of a advocate of this type of code because it's straightforward and it's not terribly complicated, and you're not really buying anything by reducing your two statements down into one. Sometimes it just adds more complexity and confusion. But now you know how those work. This is what they tell you not to do, and that is to get real complicated here. Avoid using these types of expressions. You've got an integer k is going to be equal to, and now we got a pre-increment on I plus I. That gets to be very confusing. So just avoid doing that. Prior to Java 2, all expressions can be used as statements. Since Java 2, only the following types of expressions can be statements. And you have a variable and an operator, like plus equals, and then an expression, and then where the operator is equal to the plus, the minus, the asterisk, or integer division, or the modulus function. And you can go ahead and, for instance, do a pre-increment on variable. And if variable has 3 in it, now it's going to be 4. This would, in effect, be the same as doing the post increment. If variable has 3 in it, you're doing a post increment, it'll then become 4. These are identical. These can be used interchangeably. It's only when you have an assignment statement where the pre-increment and the post increment and the pre-decrement and post decrement you have to worry about, because that is 2 steps. Those are really 2 statements. But for just a standalone statement like plus plus variable, that's just going to increment the variable by 1. Likewise, this will do the same. This will decrement the variable by 1, and this will also decrement the variable by 1. Consider the following statements. We have an integer called I. It's of the type byte, and we are assigning it to be 100, the value 100. The data type byte, to refresh your memory, is 1 byte in storage. It handles integers, and the range that it can store integers goes from -128 all the way up to +127. So this 100 does fit within that range. You won't get an overflow exception by trying to assign 100 into this I variable of type byte. Next is a long variable, k. Remember what longs are. Longs are integer variables, but they're stored not in 1 byte of storage, but in 8 bytes of storage. This is where we stored the milliseconds. So that's 64 bits. It's a rather large area in storage in which you can store integers. And the integer we're going to store is going to be the result of this calculation. I times 3 plus 4. All right, well, I is 100 times 3 plus 4. The orders of operation, the precedence is we do multiplication first over addition. I equals 100 times 3 is going to be 300. And then we're going to take 300 and add 4 to it, and this expression to the right of the assignment statement is 304. 304 gets assigned into the variable k. The third statement is a different data type. Here's a variable called d, and d is of the type double. To refresh your memory, a double is a floating data type, and it is 8 bytes in storage, and it contains decimals. It can contain fractional decimal amounts. We have I, which is currently 100, times 3.1, so we're going to move the decimal over, and, well, let's just make sure we have I times 3.1 plus k divided by 2. The orders of precedence is to do the multiplication and division. They have the same level of precedence. So when you have the same level, such as multiplication and division, the compiler will go left to right. We have multiplication here, and we have division over here. We got a plus in the middle. So we're going to do multiplication first, the left one first. I is 100 times 3.1 is going to be 310. So now we have 310 plus k divided by 2. A plus and an integer division, the integer division gets calculated first. So we have k, which I've forgotten what k is now. K is 304. We have 304 divided by 2 is going to be 152. And now we have, I've forgotten what this is, 310 plus 152 is 462. I believe I did that correctly. So this whole value here of 462 is going to be assigned into the variable d of the type double. Even though it's an integer, it can go into a double. It will be stored as a floating point. There's just nothing to the right of the decimal. It's all zeros. So here's where we're using multiple different data types to perform operations. Here are some conversion rules whenever you do that. When performing a binary operation involving 2 operands of different types, kind of like what we were just doing, Java automatically converts the operand based on the following rules. If one of the operands is a double, the other is converted into a double. Otherwise, if one of the operands is a float is a 4-byte decimal field. If one of the operands is a float, the other is converted into a float. Otherwise, if one of the operands is a long, the other is converted into a long. Otherwise, both operands are converted into ints. And an int is an integer field that was 4 bytes in length. Those are just the conversion rules. Typecasting. Let's look at this. This first, it comes in 2 different types, 2 different flavors. You have implicit casting, and you also have explicit casting. Let's look at implicit casting. We've got a double variable that's called d, and we're assigning it the value 3. This 3 is an integer. It's not 3.0, it's 3. So we are doing implicit casting by taking an integer, a literal integer, 3, and assigning it into a double variable called d. This is known as type widening. A double is 8 bytes, and an integer is 4 bytes. So you're going from a smaller area in storage to a larger area in storage. So you can think of that as widening. Explicit casting, on the other hand, would be to do the same thing. You've got a variable called I. It's going to be of type int. And we are now taking 3.0 which is a double. That would be 8 bytes, and it's also a fraction. It handles fractions. And we're going to cast it to an integer. Inside the parentheses, it says take this value here and cast it to an integer. This is known as type narrowing because we're going from 8 bytes down to 4 bytes. So it's becoming more narrow. And then you can go ahead and assign it into another integer variable called I, but you will need this int. It will disregard the fractional piece. It's only going to work with the integer piece. And here's a demonstration of what I just said. We have 3.9. That's going to be of type double. We're going to cast it to an integer. The fractional part is truncated. It means it's left, and it just assigns the integer piece 3 into the variable I of type int. What's wrong with this particular statement? Well, we have here int x equals 5 divided by 2.0. If we did 5 divided by 2.0, we know that's going to be, the result is going to be a double. And that double will not, that's going from a wider data type down to a narrower data type, and it's not going to allow you to do that. You would need to cast this whole expression, you need to cast it to an integer in order for the results to be stored into this int variable called x. Here's how the range increases. We're going to start with bytes. A byte is 8 bits. It's 1 byte in storage. It handles integers. It goes from -128 to +127. The next size for integers is short. That would be a 2-byte field, or 16 bits, in which integers can be stored. And they're obviously much larger. The next is a int data type. That would be 4 bytes in storage. That data type handles integers as well. And then long, which is 8 bytes in storage. That is also a data type for integers. And then over here we have the 2 floating point data types. The first one is a float. That would be a 4-byte float or decimal area in storage where you can store decimal numbers and fractions. And then the largest one is a double, which is 8 bytes or 64 bits where fractions are stored. Okay, the problem keeping 2 decimals after decimal points. Up until now, you've been working with programs, and the programs have had, typically, if it doesn't divide evenly, you get this very long trail of decimals. Could be 16 of them. Way too much more precision than what we need. And when you're working with currencies such as dollars, you really don't want to carry all of those decimal places. You really just want to carry just 2 decimal places for the pennies. So this program here called sales tax introduces a neat trick that you can use to remove all those unnecessary decimal places after the pennies. Let's look at the program called sales tax. Okay, we've got our package statement. We've got our import statement. We're importing the scanner glass, and we are going to use scanner input to enter a purchase amount. Let me run this so we can see what's going on here. Enter the purchase amount. Let's say I buy something for $11.75. All right, so the sales tax is, see where this is not appropriate? That's not a good example. Let's try something else. Let's try 11 even. All right, here we go. So I just purchased a pair of gloves. It's freezing. I need a pair of gloves. I bought a pair of gloves for $11. The calculated sales tax on my gloves is 65, and see all of these remaining fractional decimal places that I don't really need. This is how I really want to display my sales tax with just 2 decimal places. So let's just go through this code using this example. First thing I do is I get scanner input. It asks me to enter the purchase amount. I put $11 for my gloves. I take, using the next double method, we know it's a method because it has parentheses, and it's going to grab whatever I put in other words, the 11.00, and store it into the area in storage called purchase amount, so the type double, so it handles fractions. Next thing I do is I multiply the purchase amount times the tax rate, 0.06. That will multiply 11.00 times 0.06, store the result in tax, so the type double. Now I put out the tax. Sales tax is, I can put out the tax as it is, and I'll get this big long trail of inappropriate decimal places. The way to get rid of those is to use this technique. System.out.println, sales tax is, and now I'm going to concatenate. First thing I'm going to do is take the tax amount. What's the tax amount? The sales tax is this big long thing, 0.659999 all the way down, and I will multiply that times 100. So I have tax times 100 is now going to be 65.999999, right? I cast that to an integer. Here's my casting of the 65.9999, and it will then become 65 and truncate the 9s. So now I have 65. The last thing I do is I do division of 100.0. Need to put the 0.0 in there so it does precise division. And that will go ahead and then take the 65 and make it 65 cents, or 0.65. Then I can go ahead and put that out, and you'll see it becomes 65 cents. It doesn't do rounding. We'll do rounding later on, but for now, this does display dollars and cents a lot more pleasing to the eye than all of these unnecessary fractions or decimal places. So that's an example using sales tax. I'm going to skip over this and go just quickly into the software development process, because this is really what you need to know as a programmer. The first step in developing programs is to gather your requirements. It's called requirement specifications, and this is probably the most important thing that you do, because if you don't gather all the specifications and you don't gather all the requirements, your customer is going to want to introduce changes to you as you're writing your code. And you really can't do that, because you're going to lose a lot of time and you're going to not make your deadlines. What you should do in the requirement specifications phase is to talk with your customer and get all the details, all the specifics, and get it documented, and get the customer to sign off on it, and get you to sign off on it, and then you go ahead and you start coding it. You design it and code it and all this other stuff. If they have any other additional ideas as the development process continues, well, you know what? You got to tell them that's part of change control, and we'll address that after I'm done and see whether or not you want to pay for any future changes. All right, so requirements specifications is probably the most important. Make sure you get everything nailed down and agreed upon by the customer. Next, you do your systems analysis. How is this particular solution going to run? Is it going to run on a mainframe? Is it going to run on a PC? Is it going to run on a Chromebook, an Android phone, an iPhone, on the web? What's the system that this is going to run on? Once you determine that, you do your system design for your solution. The implementation phase is where you write your code. The testing phase has a bunch of tests to it. The first test is obviously your unit test, just like what we did earlier when we tested the current time in milliseconds. When I introduced a change to make it Norwalk time in AM or PM, I had to go through many different test scenarios where I hard-coded the current hour. And if you're working on something else, you may also, on a different type of program, you may want to also have integration testing. Integration testing is when your program now gets run with the programs in the process that your program is running in, the surrounding programs, making sure it runs inside your online system, for instance, or in your batch processing. You can also test for stress testing, for volumes. If you have 100,000 users banging on your program, well, do you have enough memory to handle all that? Do you have enough computing power? So that's called stress testing. There's also a thing called regression testing, where you go ahead and make sure that things go backwards as well as forwards, if you want to back things out. And then there's also the deployment phase, where you take your finally thoroughly tested solution and you roll it out to all the end users. It could be one person, it could be 100,000. And part of the deployment process is to also develop user manuals, help guides, help screens, help web pages, whatever it may be. After all, if it's a large application that you've developed, there's going to be a lot of end users and they're going to need help. This whole process, from requirements down to deployment, requires that when you make estimates that they have enough buffer in them to handle all these different steps in the development process. And normally, if your development time is 50 hours, you may want to give your customer an estimate of 100. Put in plenty of buffer, because all of these steps along the way do take up time, which you have to charge your customer. The last step in the software development process is maintenance, which is where you do most of your coding. In my career, I've done probably 80% of my coding in the maintenance phase. The maintenance means you've got to introduce change into existing programs, not writing programs from scratch, but actually fixing or changing or enhancing existing programs. And many programs I worked in, they were 20 years old or more. It's very costly to rewrite a system. As anyone that might know that went through Y2K in 1999, that's where many systems had to be rewritten because of the year problem. So maintenance is usually what you're going to be working in, because people don't want to write systems from scratch or rewrite systems. It's very, very costly and takes a lot of time. Okay, so that's the software development process. We can skip over all of this. I'll quickly go through compute loan. This program lets the user enter the interest rate, the number of years, the loan amount, and computes monthly payment and total payment. And here is the formula. You've got a monthly payment equal to this: the loan amount times the monthly interest rate all over, in the denominator, 1 minus 1 over 1 plus the monthly interest rate raised to the number of years times 12. It's a very complicated formula. The finance department came up with it, but this is how you can calculate your monthly payment on any loan that you choose to take out. What's that program called? It's called Compute Loan. All right, let's run this so we can see how it works first, and then we'll kind of step quickly through the code. Enter the yearly interest rate, for example, 8 1/4. Let's say I want to buy a condo down in Norwalk for, I don't know, $200 and something thousand, let's say. So I want to go ahead and enter a yearly interest rate. The current interest rates are pretty low right now. Let's just say it is, I don't know, 3.75. That's my current loan rate. If I go to a bank, how many years do I want to borrow this for? I'll get out a 30-year fixed mortgage, so I'll put 30 in. The loan amount, I want to borrow $200,000. I'll try and put down $40,000 to avoid PMI, which is mortgage insurance, which costs me more. So if you can put 20% down, that's good. So I'll borrow $200,000, and this quickly calculates that my monthly payment is $926.23. Is that something that I can afford? If it is, then I may want to go through with the loan. If not, I got to go ahead and find a lower interest rate or not borrow quite as much. The total payment, here's an interesting calculation. The total payment on a $200,000 loan after 30 years, I've paid back $333,443.22. As you can see, it's quite a bit more than what I originally borrowed. That's how the bank makes its money. Now, let's see how this program calculated this. Well, you might want to go ahead and do that algorithm development that we talked about before, lining up all the steps and then coding each step. Here is where you have your line comments describing each of your steps. Enter the yearly interest rate, for example, 8.25. I put in 3.75. It's a double, so I'll use my next double method. I'll store it into annual interest rate. Next step is to go ahead and do integer division of annual interest rate divided by 1,200. Why 1,200? Well, because I put in an annual interest rate, and I need to bring this down to a monthly interest rate. And I also put it in as 8.25. I wanted to make it be a fraction, so I'll have to move it over the decimal place 2 to the left, which in effect is multiplying this whole thing by 1,200. Next, enter the number of years. This is an int, so I'll use the next int method. I'll store that into an integer variable called number of years. Here's the loan amount. I'll get that amount, 200,000, as a double using the next double method, and I'll store it into the loan amount variable. Calculate the amount. This is this big mess that I showed you before, the monthly payment over here in this whole thing. Monthly payment is equal to this. I have to somehow figure out how to express this in Java code. And this is the expression, loan amount times this whole big thing here. Notice I am using the math.pow method. The math.pow, the pow is a method in the math class. We know it's a method because it has parentheses. It begins here and ends here. There are 2 parameters. The first parameter is the base. That's the base. And then the next is the exponent, number of years times 12. It takes those 2 parameters. When they get values in them, they become arguments to this method, and the pow method will then calculate that calculation and put it into this overall formula, and then it will get assigned into monthly payment. And then the last thing that we do is we just display the results. The monthly payment is, and now you're going to do this method that we described before, where we take the monthly payment times 100 divided by 100.0, and that will get rid of the unnecessary decimals and express it as currency, cast it to an integer, and display it like that. And also the total payment is, and the same technique is used down here for the total payment. And you have 23 cents and 22 cents rather than this big long trail of decimals. Okay, that's compute loan. I got one more here, and that is compute change. It's nothing more than what we already kind of did. Close this project, open compute change. And this is rather repetitive, so I'm not going to go through it. But what this does is it says enter an amount in double, for example, 1156. I'll put 1156. And a dollar amount of 1156 is $11, 2 quarters, no dimes, 1 nickel, and 1 penny, and that adds up to $11.56. So this calculates all the different coins and dollars that you would need to produce. And it's the same technique. You're using integer division and the modulus function to capture these amounts. Okay. The rest are common pitfalls and errors. I'm not going to go through these. You should go through them just to see if you're committing these so that you can avoid doing this. And there's just a few of them. Maybe you have hit a few of these in your experiences. Now what I want to do is go over the lab for this week. We have a holiday on Monday, so this lab will not be due until Wednesday. But after Wednesday midnight, it will go to a 0. I would strongly suggest you knock out this lab. Many have done it already. It's not that difficult. It is a restaurant. Let's make this larger. A restaurant bill. Lab number 2 says to write a Java program that calculates and displays a restaurant bill. The program will prompt the user to enter the price of an appetizer, a dinner, and a dessert. So you got a 3-course meal. Your program will declare the following constants. You've got a low tip rate, a medium tip rate, and a high tip rate, 10%, 15%, and 20% respectively. You also have a Connecticut state sales tax rate of 6 3/35, or 0.0635. You should have variables for appetizer price, dinner price, dessert price, total prices, total tax, total bill, low tip, medium tip, and high tip. Use these variable names in your solution. These are appropriate using the proper convention. They're fully descriptive, so use each one of these variable names in your program. Declare all variables as double data types to format your output so that it prints properly. You should use a \T escape sequence to tab over. If you want to tab over twice, you can use \T. You can stack them up. You want to use 3 \Ts to tab over 3 times, that's fine too. You must space down a line after the meal amounts are entered and after the total bill amount. See the sample run below for the tip recommendations. All dollar amounts must be aligned neatly with the dollar signs and displayed to 2 decimal places. So you'll be using that example, that sales tax example. We're just going to display down to the penny, nothing more. Unnecessary decimal places after the pennies will be removed. You can use that technique in the sales tax Java section. Be sure to include a program header block similar to the ones you've used in previous assignments, and your output should be formatted exactly as the sample run below. You go to a restaurant, okay, and you enter the price of your appetizer, $8.99. Enter the price of your dinner, $23.96, and the price of your dessert is $13.94. Your program captures these 3 using scanner input, and it now produces the following restaurant bill. Your appetizer price was $8.99. Notice how it's nice and neatly aligned with dollar signs. Next is your dinner price, $23.96. There's the dessert price, $13.34. You calculate your Connecticut tax as $2.93, and your total bill for the evening dinner was $49.22. Space down a line. You can use the \N escape sequence. And then you have tip recommendations. Well, a low tip or a 10% tip on $49.22 would be $4.92. A medium tip is 15% or $7.38. A high tip is 20%, $9.84. Zip that as Lab 2 and then send it to me as your name, Lab 2, as an attachment in Blackboard. That is your lab for this week. It will not be due on Monday. It will be due on Wednesday, but I strongly suggest you get it done before the weekend. Next is the in-class that I just assigned today. For those of you that are in class, for those of you that are doing it online, it's referred to as a pre-lab, but they're essentially the same thing. And I'll describe that as well. Now that you're an accomplished programmer, your needs are sought after all over the world, and you're doing a lot of traveling, and your poor daughter is struggling with her math homework. So you're not around to help her because of all your travels as a world-renowned programmer. So you're going to write a program to help her check her work. Your daughter's homework is below. She wants you to write a program to help her correct her answers while you're away. Here is what her math teacher gave her. The math homework is find the areas of the following rectangles and circles. The math worksheet has rectangles numbers 1, 3, 5, 7, and 9. And circles, the areas of the circles, are numbered 2, 4, 6, 8, and 10. So you quickly notice that all the rectangles are odd-numbered assignments, and all the circles are even numbers. And notice that for the area of a rectangle, you need length and width, and for a circle, all you need is radius. The rest is pi, which is 3.14 you can use. All right, so that's your daughter's math assignment. Here is the solution flow-charted. There are two ways that you can go ahead and break a problem apart and then start writing the Java code. The first that we described was the algorithm process, where we broke the milliseconds to get the current time. And we stepped that through seven steps, I believe. There's another way that you can go ahead and tackle a problem and break it into its parts, and that is using flow charting. There is a section in Blackboard called Visual Logic. Visual Logic is a tool that allows professors to get across to his or her students how to solve a particular programming problem other than algorithm development using flowcharting. And flowcharting symbols look similar to this. In this particular case, we'll step through this. What your solution should be in this in-class assignment is to get some input. A right-leaning rectangle or parallelogram indicates that we're going to get some input. So here's a right-leaning rectangle, so we're going to get the problem number. Remember that the odd problems are rectangles and the even problem numbers are circles. So the first thing we're going to get from our daughter is the problem number. Then we're going to ask a question. A diamond-shaped flowcharting symbol indicates that you're going to ask an if or a selection statement. That's next chapter, chapter 3. The question we're asking, is the problem number greater than 10, or is the problem number less than 1? If that's the case, then your daughter has entered a wrong problem number. The problem numbers can only be between 1 and 10. If it's the case, if it's a true, then it's outside the range. You're going to go ahead and put out problem number is outside the range and end the program. And here's your flow chart that expresses that. If the problem number is within the range, it's 1 through 10. Now you're going to ask another question. This diamond-shaped indicates that this is an if question. Is the problem mod 2 equal to 0? This mod is a function in Visual Logic. It's identical to the remainder function or the modulus function, the percent sign. And this says if whatever number was entered, let's say the number was 8. 8 mod 2 is going to be equal to 0 because it's even. Division by 2, if the remainder is 0, we know it's an even number. Otherwise, it's an odd number. So if it's 8 and its remainder is 0, then we're going to take the true branch and say it's a circle. We'll output circle. This is a left-leaning parallelogram, which says it's output. The right-leaning indicates input. The left-leaning indicates output. So we're going to output a literal string called circle, and then we're going to get some input. I need the radius. So we'll ask our daughter, what's the radius? And then we're going to output the expression. Area equals pi r squared, 3.1415 times the radius times the radius. And then end it. If, in the case, your daughter enters 7, Well, 7 modulus 2 is going to be equal to 1, and therefore it's not equal to 0, so we'll take the false branch, and we're going to conclude it's a rectangle. We will output the string rectangle. We're going to get some input. We're going to need the length of the rectangle. This is my variable name, length r, and I need another variable, width r, where I get the width from our daughter. Then you calculate the area, which is going to be equal to the length times the width, and put that out. So that's a very simple flow chart, but it gives you an idea as to how the symbols look, and oftentimes people prefer flow charts as opposed to algorithm development because they can actually see how the program flows, especially as you start getting into selection statements and loops. It's harder to see in algorithms where you have just steps. So this is the introduction to flow charting. The beauty behind visual logic is you can actually run this flow chart and see if, in fact, it's processing correctly. All right, so that's a flow chart, and here's how I ran the problem in visual logic. Enter your problem number. Daughter enters 1. It's a rectangle. Enter the length, 10. Enter the width, 20, and the program will produce area equals 200. Run it again. Enter your problem number. This is 2. Oh, that's a circle. Enter the radius, 10. The area is equal to 314.159. Enter your problem number 11, and that's when your program takes this branch. It's outside the range, ends it immediately, and says the problem number is outside the range, program ending. So I've tested my flow chart using visual logic. Here's your assignment. Essentially, it's this. It's just a restatement of what I just described. Write a Java program called in class 3 that prompts your daughter to enter her problem number. If an even integer is entered, your program should calculate the area of a circle. You will need to prompt her for the radius of the circle. If it's an odd integer entered, then your program should calculate the area of the rectangle. You will need to prompt her for the length and width of the rectangle. Use selection statements to code this. That means use the if statements. If, then, and I just gave you a little diagram here that the area of a rectangle is length times width, and the area of a circle is pi r squared. Declare a variable called probnum as a byte data type, because that can handle negative 128 all the way up to positive 127. So our only problem numbers are 1 through 10. So that should certainly handle your daughter's entry. The length and width and radius variables should be declared as double data types. Use the logical OR operator to validate the range. Read that in Chapter 3, what a logical OR operator is, to determine whether or not the problem number is less than 1 or greater than 10. And you'll see in the chapter how to do that. If it's outside the range, you can issue a return statement. So if it's outside the range, just type in return semicolon, and that will end your program. Your output should be formatted identical to the sample runs below. Be sure to include a program header block similar to the one below, and I've given you that right here. Make sure you put your name in as author. I'm getting students who are keeping me as the author. That's not right. Here's some sample runs. Your daughter is prompted to enter her problem number. Problem number 1, that's a rectangle. Enter the length, 10. Enter the width, 20. Area is 200. Program ends. Daughter runs it again. Now she's doing problem number 2. Well, that's a circle. Enter the radius, 10, and the area is equal to 314.159, and it ends. Last run is where you go ahead and enter your problem number 11. Problem number is outside the range, program ending. Please rename your folder as your name in class 3. For you online guys, it's going to be your name pre-lab 3, and send it to me as a zipped file in Blackboard. Those are your assignments so far. Are there any questions? I've gone through an awful lot, but hopefully that helps certainly the online guys that don't get classroom interactivity, or if my class. Yeah, go ahead.
Okay. Within the trying to enter the trying to find the area and the width. You mean like just to put the double and put the names right next to it, and to declare the area for the up top above it, or?
Yes. What you should do in organizing your programs, you normally like to put all the variables that you're going to be using at the top of your program and declare them as doubles or ints or bytes or whatever they may be. And then you get your scanner input, and then you go ahead and use those variables that have been declared to calculate all the different things you need to calculate.
Hey.
Okay? I mean, just follow the flow chart. The flow chart is probably very easy to follow, and just write the code that corresponds to each box in the flow chart.
Okay.
Okay, Mike, does that help?
Sort of, yeah.
Okay, any other questions? And it could be any question on anything. Chapter 2, your lab, your in-class. Are we all good? If we're all good, we can call it a night. Okay, I'm not hearing any. Go ahead.
I don't know how many. Someone about to say something?
No, I was just waiting for any questions before we call it a night.
No questions.
I guess we have no questions. Okay, excellent, terrific. All right, then we'll call it an evening. That'll be the end of the webinar. All of you have a great break. Okay, enjoy your time off. Bang this code out, get it done with so it's not hanging over your head, and enjoy your long weekend. And for you guys in class, we'll see you on Wednesday. And if there are any questions for you online guys, you can send me messages, Blackboard messages, all throughout. I don't take any breaks, so you can send me any questions anytime you want.
Thank you.
Okay. Have a good night, guys. We'll talk to you soon.
Good night. Thank you, Professor.
Bye.
Okay, good night.
Bye-bye.
Bye now. The recording now, and as is with all these webinars, I do need to announce the webinar disclaimer. This WebEx service includes a feature that allows audio and any documents and other materials exchanged or viewed during this session to be recorded. By joining this session, you automatically consent to such recordings. If you do not consent to the recording, please do not join or participate in the session. This WebEx service is intended to supplement the classroom experience. Duplication or redistribution of lecture capture recordings is prohibited without appropriate consent. All right, what I want to talk about is essentially Chapter 3. And before I do that, I spent a good part of today grading everyone's labs for lab number 2. And I thought I'd just go over some of the feedback that I'd like to give you on what I found that I saw consistent people doing that needs to be corrected. Number 1, make sure you have the correct file names. I'm not seeing this abused too frequently, but I do see incorrect file names. If I ask you to call your project Lab 1, I don't want it to be called Restaurant Bill. I want it to be called Lab 1. All right, so please keep that integrity there. Please use proper naming conventions. I even specifically said in the lab, please call the variables these names, and people chose to choose their own names. I have a reason for why I want to do this. Oftentimes you're working on a big project with many other people, and they rely upon the variable names that you have been told to use so that they can use similar or corresponding or sticking to the same convention in their programs, so that when you integrate, as we discussed, I guess last week, in integration testing, it's easier to test when you have like a consistent set of variable names. So if I ask for something in a lab, I'm really going to be sticking to seeing that you guys do it. And obviously, if you don't, I'm going to take some points off. Appropriate indentations. I'm still seeing indentations kind of floating all over the place. I really want you to spend the time to indent your code according to the conventions that we talked about in the earlier chapter. I'm still getting just Java source code. And I'm going to start losing my patience on this because this really slows me down. You need to send the entire NetBeans package zipped, not just the source file. I can't do anything with the source file. I need all the other pieces. It's like sending me the engine to your car and saying, how does it run? I can't determine that until I put it in the car and give it a test drive. So please send me the entire NetBeans package zipped. Number 6, oh no, it's number 5, documentation, header block, and commenting. Please do use appropriate commenting. Some of you are still not putting a documentation header block in there. I'm going to start taking more points off. It is critical that you do that. It helps me to know who I'm correcting as I'm grading these, as I'm juggling all these other different things. And it's also going to be used in your future for any programs that you write for any business that hires you. Number 6, very, very important. Please focus on the assignment details. I take great pains to write these assignments up, whether they're in class or whether they're labs. In class is intended to give you a warm-up for the lab. I'm not grading the in class or the pre-lab if you're an online guy, but I do want you to follow my instructions. I will take points off in the lab if you do not follow my instructions specifically. You can't cut corners, you can't abbreviate, you can't change the variable names if I specifically ask for that. I'm going to pretend like I'm the customer. And if you go ahead and not give the customer what the customer is asking for, you won't be a customer for that customer for very long. So I'm kind of prepping you for that. Please focus in on the assignment details. Focus on thorough testing. In the case of the restaurant bill, I did not see many people testing their final bill. Now, I don't know if you ever went to a restaurant, but if a customer walked out and the bill didn't add up right, or the tip recommendations weren't calculated correctly, you might have a problem going back to that restaurant. So the manager might have a problem with hiring you to write their restaurant bills. So please understand that you need to thoroughly test your code before you submit it. I am still getting some submissions that don't compile. And I'll tell you right now, if an assignment is submitted and it doesn't compile, it's going to be -20 right off of the bat. You're going to start with an 80. And if I feel like correcting it after that, it's just going to keep going down and down. Because it's very hard for me, especially as the assignments get more and more challenging, to figure out whether or not you actually thoroughly tested this code and whether or not it actually works. And then last but not least is number 8. Many of you are still submitting your assignments right near the deadline. And I'm just saying you're flirting with disaster by doing that. So please do not put these assignments off, certainly not the labs. Okay, having said that, I hope my voice can get through this. I've been coughing and flat on my back for the past 4 days now, so I hope it gets through this session. All right, the motivations for this chapter 3 If you're assigned a negative value for a radius in listing 2.2, compute area with console input.java, well, everybody knows that a negative radius doesn't exist. The program would print an invalid result. The area would be something that would be negative. If the radius is negative, you don't want the program to compute the area. How can you deal with this situation? In a real-life situation, if you have bad data coming in, we're only working with one program or one iteration of data. But imagine if you were processing 100,000 records coming in, and it was a bad file, and it took an hour to process, and it was a bad file, and you processed that for a full hour, and all you were doing was processing garbage. You've just wasted an hour. So what you want to do is you want to test right up front, are you getting bad data? And if you're getting bad data, then you need to act upon it immediately, so you don't waste an unnecessary hour of processing time on data that's not going to be used, on the results of the data processed. It's not going to be used. So how do you deal with this? First thing we're going to talk about is the Boolean type and the Boolean operators. Okay, Mike, you got a question? Take yourself off mute. It's Michael K. Michael K., do you have a question?
Yeah. Well, then my question about thinking about the assignment, I'm explaining about the calculation, even though I thought the integer sometimes, you mentioned estimates the numbers I mean, it could have been like rounding to the nearest number, but I thought trying to make it, I don't know how many digits that it has to be, but when I tried to do that, it kept, it didn't show the exact number of price. And why did you tell me?
All right, Michael, this is Michael Shiro. Michael K is the one that raised his hand.
Oh, my apologies. I didn't know. I thought you mentioned me. Okay.
Michael Shiro, please. Michael, we're gonna take that offline, okay? If you have any questions regarding your specific lab submissions, we'll take that offline. You can send me a Blackboard message, okay?
My apologies. Thank you.
Okay, Michael K., did you have a question? Okay, I guess he pulled his hand down. All right, so we're talking about the Boolean operators and the Boolean type. There was a guy, George Boole, back in, I think he lived in the 1800s, and he's kind of like the father of this whole notion of binary computing. And often in a program, you need to compare two values, such as whether I is greater than j. Java provides 6 comparison operators, also known as relational operators, that can be used to compare two values. The result of the comparison is a Boolean value, and a Boolean value can be true or false. It's basically a binary notion. This is a statement. It's a Java statement right here. And it says we're going to declare a variable called b. It's going to be of the type Boolean. Now, we've declared variables before of the type int and type double, type char, type short, byte. Now we're going to introduce the type Boolean. And this variable b is going to be assigned the results of this expression. This expression is 1 greater than 2. Well, when you think about that, 1 greater than 2 is false. That is not true, so it's false. So the value for b would be false. A Boolean can only be true or false. In this particular statement, the value for b would be false because of the resulting evaluation of this expression. Here we have the relational operators. We have a Java operator, the less than sign. The mathematical symbol is the less than sign. And here's an example, radius less than 5. I'm sorry, radius is less than 0. And the result is false. Less than or equal. In mathematics, they put the little line underneath it. And the way you would write that in Java is the radius less than or equal to 0. And hopefully the result of that would be false. The next Java operator is the greater than sign. It's the same as in mathematics. It looks like that. And the radius greater than true, greater than 0, hopefully it will be true. In Java, we write greater than or equal to this way. In mathematics, you write it this way. And this is what the expression would look like, which would yield a true. This is the equivalency operator. It's a double equal sign. In math, it's the equal sign. It means equal to. And what we're saying here is the radius equivalent to 0. This is not an assignment statement. This is an equivalency operator. And we're saying, is the radius equivalent to 0? And hopefully it'll be false, because that wouldn't be a circle. And then the not equals in Java is written like this, the exclamation point followed by the equal sign. And in mathematics, it's the equal sign with the slash through it. If you would say the radius is not equal to 0, well, if that's the case, then it's true. We're not taking care of the fact that if the radius was less than 0, but in this case, we'd just be looking to see if the radius is not equal to 0. So those are your Java operators. Those are your relation operators written in Java. Let's take a look at this simple little addition quiz. This example creates a program to let a first grader practice addition. The program randomly generates 2 single-digit integers, we'll call it number 1 and number 2, and displays a question such as, what is 7 plus 9 to the student? After the student types the answer, the program displays a message to indicate whether an answer is true or false. I've got it queued up right here. So here is, let's make it a little bit larger so we can see it. Here is our addition quiz program. And the first thing we're going to do is generate 2 random integers, number 1 and number 2. We're going to use the current time millis method in the system class, and we're going to do a modulus 10, and then we're going to do a integer division 7, modulus 10, just to give it a little bit of a twist, but they're basically doing the same technique, and you're going to get 2 different random integers between 0 and 9. The next thing you're going to do is you're going to create a scanner object. It will be called input. And we're going to ask for 2 numbers. What is whatever the first random number is, plus whatever the second random number is. And then we're going to get, using the next int method in the scanner object, input, and we're going to assign the student's answer into the variable called answer of type int. And then we're going to print out the results. Whatever the number is, plus whatever the second number is, equals answer is, and here's where we have the expression where it will get evaluated to be either true or false. And it gets evaluated because of this equivalency operator. Is the answer equal to number 1 plus number 2? If it is, this overall result will be replaced with true. Otherwise, it will be replaced with false. Let's play the game. All right, the first question is, what is 0 plus 4? I'll say 4, hit enter, and here is where this came back out and said 0 plus 4 is true. 0 plus 4 equals 4 is true. So this gets evaluated to true. I'll do it one more time incorrectly. 6 plus 6 equals 11. And this will get evaluated to be 6 plus 6 equals 11 is false, because 6 plus 6 equal to 11 is false, and that's what gets displayed. Okay, one-way if statements. Boolean expressions are what get put inside, are what get put inside an if statement. So you see this parentheses here, and inside the parentheses there is a Boolean expression that's going to evaluate to either true or false. And depending upon whether or not it is true, if it is true, the code inside this curly brace and this curly brace will get executed. If the Boolean expression is false, then it's going to skip over this block of code and execute the next instruction or next block of code. Here is the flow chart for this. The diamond shape is a select statement or an if statement. And hold on just one second. Oh, okay. Yeah, I'm on a webinar right now. Maybe a couple hours. Yeah, I'm talking right now. Yeah. Right. Okay, back to the flow chart. So this diamond shape is a decision block or an if statement. So this basically represents a Boolean expression for an if clause. And if the clause inside this parentheses is true, you take the true branch. Otherwise, you would take the false branch. Here's an example in Java code. If radius is greater than or equal to 0, well, this is going to be evaluated to be equal to 0. It's greater than or equal to be 0. If it's true, then we're going to execute from here down to here. And that will avoid us calculating the area of circles that have negative radii. So this will only execute from here down through here if this radius is greater than or equal to 0. And we're going to calculate the area is equal to pi r squared and print it out. Okay, this is wrong. This is correct. You need to put parentheses. Don't forget the parentheses like this because it will not process. If you have questions, was that Julio? Do you have a question, or because I'm seeing things pop up, and if you have a question, I would prefer you just kind of coming off of mute and just piping right in, because it slows me down if I have to read things. Julio, did you have...
I was responding to, I think it was Drake who posted a question.
Okay, all right, okay. If you have a question, sometimes you can respond directly to that person, and then I think I don't see it. But anyway, the point behind this slide is basically make sure you put parentheses here. This right here is the equivalent of that. What this is saying is that if I is greater than 0 and you have a block and there's only one statement inside the block, you don't need the curly braces. So they've removed the curly braces and said if I is greater than 0, well then execute the next sequential instruction. Otherwise, skip over the next sequential instruction and go to the one after that. So if I is greater than 0, we're going to go ahead and say I is positive. If I happen to be negative 12, if negative 12 is greater than 0, it's false. It's going to skip over system.out.println and it's going to go to the next instruction. You do not need those curly braces when you have just one statement for the truth branch. Okay, how about a simple if demo? Write a program that prompts the user to enter an integer. If the number is a multiple of 5, print high 5. If the number is divisible by 2, print high even. All right, so here's the code. I'll run it. It says enter an integer. 4. 4s, it's high even. Okay. Let's run it again. And I'll do 20. It came back and said high 5 and high even because it is a multiple of 5 and it's also even. So how's this working? Well, we're getting an integer from the console. We're putting it into the variable number. And then we're doing a modulus 5 on number and asking, is it equivalent to 0? Don't forget when you're writing your code to put double equal signs. I know it's a tendency for everyone to forget that, but you need to make sure that you put in double equal signs. This is the equivalency operator. It will yield a true and false. If you do not put a double equal sign, it's going to be an assignment operator. And it's going to take whatever's on the right-hand side and assign it into what's in the left-hand side. And then it's going to evaluate to see whether or not it's true or not. It's going to be unpredictable. So you don't want to omit that second equal sign. So number, what did I use? I used 20. Okay, 20 modulus 5 equivalent to 0? Yes, because there is no remainder when you divide 20 by 5. So it's going to print out high 5. That's for that if statement. Now we're going to execute the next if statement. If 20 modulus 2 is equivalent to 0, it is because there's no remainder. We're printing out high even. So here's some simple examples of a simple if statement. A two-way if statement. If, for example, you have a Boolean expression and it's true, you execute these statements if they're true inside the block. A two-way statement would have an else clause to it, and after the else, you can go ahead and put curly brace, and if this particular Boolean expression is false, it will not execute what's inside this true block, but it will execute what's inside the else block or the false block. And likewise, if you only have one statement in your else, you don't need the curly braces. Here's the flow chart. You have a Boolean expression. If it's true, execute the statements that are to be processed when true. When it's false, execute the false ones. Okay, here's an example. If radius is greater than or equal to 0, right here, we have this curly brace going all the way down to this curly brace. And this looks like it's going to go ahead and compute the area of a legitimate circle that has a radius greater than or equal to 0. And print it out. Else, now we're going to go ahead and print negative input. So you're not going to waste your time processing all this. You're just going to print out negative input. And you really don't need these curly braces because you only have one statement in here. So you could just eliminate this curly brace and that curly brace, and everything would process identically. Multiple alternatives of if statements. Here's one way you can go ahead and determine how to determine a letter grade based upon a numeric grade. Here we have if a score, some variable, let's say score is of the type double, and you want to know if score is greater than or equal to 90.0, well, if the score is 99, then it'll take the true, which is the next sequential instruction, and print out the person got an A. Else, it would do nothing. So we would drop through this. But let's say the person got an 89. Ask the question, if the score is greater than or equal to 90, That's false, so we're not going to do this. The person got an 89. Now we do the else, and we're going to add another if to this. Else, you can ask, is the score 89 greater than or equal to 80? Well, it is. 89 is greater than or equal to 80. So we'll print out B and then fall through because the other else's don't apply. Likewise, 79. It's not greater than 90. It's not greater than 80. It's greater than 70, so you print out C. You continue on all the way down, and you can derive letter grades based upon using if, else, all the way down to the F, where you just conclude if the score is greater than or equal to 60, and it's not, well, then you got something that's below 60. This is better than indenting and having a staircase type look. This makes things a little bit cleaner to follow. So that's the recommendation that the book tells you to use. Here's the same, whoops, let's go back. Here's the same thing in a flow chart. I'm not going to go through it again, but you got the idea. But this is how you would ask the questions using all these decision blocks. Here's your true branches, and here's your false branches. Eventually, it becomes an F. First one is an A. I already went through this, so I'm not going to go through that. Okay, the else clause matches the most recent if clause in the same block. Okay, be very careful of that because it doesn't have, you got to be careful with your indenting. This else here matches this if. Even though you lined it up under this if, it's really going to be aligned and associated with this if, not that if. That's why this is better, to make sure your indenting is appropriate when you start using if and else's, and especially these nested ifs, when you have an if within an if. All right, let's see if we can follow this thing here. Nothing is printed from the preceding statement. To force the else clause to match the first if clause, you must add a pair of braces. All right, we got I is 1, J is 2, K is 3. I, J, K, 1, 2, 3. All right, if I, which is 1, is greater than J, that's false. So we don't go here. We need to make sure we put our braces in, and we will do the else, and then we will quickly see that we're going to print out B. The statement prints out B. Very important that you put your braces in the right spots. Adding a semicolon at the end of an if clause is a common mistake. Don't do this. This essentially basically just wipes out the if clause, and everything else is nothing more than a statement that will get executed. So here's a tiny little mistake. You're going to get into the habit as you write more and more Java code to just through habit, you're going to go ahead and hit that semicolon key. That's why the same line is where the curly braces have become the tradition to avoid that. This mistake is hard to find because it's not a compilation error or a runtime error. It is a logic error. This error often occurs when you use the next line block style, which is why pretty much the industry has gotten away from this and opted to have it on the same line. Okay, here's a tricky little thing here. If number modulus 2 is equivalent to 0, well, then we're going to assign the value true into the variable even. And even presumably is a variable of the type Boolean. Else, even is going to be assigned false. This statement, this series of statements, is the same as this thing here, where we're declaring even as a Boolean, and we are doing this expression. Number modulus 2 equivalent to 0. I don't know what number is, but let's say it's 4. 4 modulus 2 equivalent to 0. If that is true, in fact, 0, which is true, then even will get the value true. You can use either approach. You can say if even is equivalent to true and print out it is even, or you can just put in parentheses, even. This will get evaluated to true or false. So you don't have to go ahead and use the equivalency operator when you're working with Booleans. You can just put in parentheses the Boolean, and it will evaluate itself to be either true or false. If it's true, it executes the next sequential instruction. All right, this example creates a program to teach a first grader how to learn subtractions. The program randomly generates two single-digit integers, number 1 and 2, and with number 1 greater than or equal to number 2, and displays a question such as, what is 9 minus 2 to the student? After the student types in the answer, the program displays whether the answer is correct. Let's look at subtraction quiz. Okay, notice these programs are not very long. There's a lot of I put a lot of comments in here, so if I took all the comments out, it would be very, very short. But they can get very complicated. As we start working with ifs and Boolean logic and nested ifs and some of these relational operators, it can get very, very confusing. So let's go through it kind of carefully. It's also a good idea to put comments in. I use line comments here because it's not always apparent what you're driving at when you are writing code, especially using Boolean operators. Well, this one is obvious. We're generating two random integers between 0 and 9. In this case, we're using the random method from the math class, and just to focus in on that, what the random method does is it returns back the fractional second from the system clock. So whatever that fractional second is, it will get multiplied times 10. So for instance, if it returns back the fractional second 0.1, 2, 3, 4, 5, 6, 7, 8, 9, well, when you multiply 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and you multiply it times 10, it's now going to be 1.2, 3, 4, 5, 6, 7, 8, 9, etc. So that now gets casted, that 1.23, it gets casted to an int, and now we're just going to have 1. And then 1 gets assigned into the number 1. We do it again for number 2. However, now it goes to the system clock a nanosecond later, and it gets the system clock, and it returns back the fractional second from the system clock using the random method from the math class. And let's say that is 0.234567891, or 0.23456789565, whatever, keeps on going. And then you multiply it times 10, well, that's going to be equal to 2.3456, etc. When you cast it to an integer, it takes the integer piece, which is 2, and assigns that into number 2. So we've basically taken two random integers using the system clock to generate a number between 0 and 9. You can also use the current time in milliseconds method, which we used earlier, but this is a new way to do it, so we're going to use it that way. All right, the second step. If number 1 is less than number 2, we need to swap them. After all, if I said to this, what is it, first grader? If I said, what is 1 minus 2? The first grader is going to get completely confused. So we need to make sure the first number is the bigger number. We can use an if statement. We can use a selection statement. If number 1 is less than number 2, well, then we're going to go ahead and flip them, right? What we do, we want to make sure that number 1 is greater than number 2. And the way to do that is to create a temporary variable to hold number 1. So we create a temporary variable, it's a hold variable, and we move number 1 into the temporary variable. Then we take number 2 and move it into number 1. And then once 2 is in number 1, then we can take what's in the temporary variable, which was the old number 1, and then we put that into number 2. And that essentially flip-flops the numbers. So now we have number 1 being larger than number 2. Now the first grader is not going to get confused. Third step, print out what is number, whatever it is. Let's print this here. Let's run this. All right, so it generated 6 and 1. It put 6 as the first one, and 1 as number 2. This is number 1 is 6, and number 2 is 1. And it says, what is 6 minus 1? And now we get from the first grader using the next int method from the scanner class. And we're going to go ahead and assign that into the variable called answer. And now we're going to use that technique that we just went over and say, if this expression right here, number 1 minus number 2, that's 6 minus 1, is equivalent to the answer that we got from the first grader, well, then we're going to say you are correct. If not, then we're going to go ahead and say, this is one statement, so we don't need curly braces. We're going to say you are wrong and give them the correct answer. So I'm in the middle of something here. So 6 minus 1, I'll say 3 in error, and it doesn't execute this because this is false. So it hops over this instruction, and it goes to the next sequential instruction, which is right here, and it prints out your answer is wrong. 6 minus 1 should be 5. Everyone, I hope, understands how that whole thing works. It's a good example of using Booleans and if statements, selection statements. I'm going to skip over this body mass index thing, but I think everybody understands how that thing is. And basically, everybody's got a body mass index, and it's calculated by, I guess, your height and your weight and a bunch of other factors. And then if your BMI is less than 18, you're underweight. If it's 18 to 25, you're normal. Excuse me. 25 to 30 is overweight, and less than 30. If the BMI is greater than 30, then you're obese. I'll have you take a look at that because that's just too lengthy to go through on a webinar. As is this tax thing. I'm not going to go through that either. All right, logical operators. We have here the logical operator, the exclamation point. In Java, that is the not sign. Its descriptions, they say, is logical negation, but it basically takes the opposite Boolean value of what exists. This is the AND operator. the double ampersand. This is the logical OR operator, the double bar. And here is the exclusive OR. It's an upward caret. And we're going to go through some examples of how to use these things. Here's a truth table for the NOT operator. Let's say we have a Boolean variable called P, and we assign it a value of true. Well, if we go ahead and put a not sign in front of that P, that now becomes false. And likewise, if we have P set to false, and we put a not sign in front of that, it will then flip it to its opposite and make it true. Here are two examples. Age greater than or equal to, greater than 18, the not sign. If, let's see. Okay, here we go. Example, assume age equals 24 and weight equals 140. So let's evaluate this. We'll go with inside the parentheses first, and we're going to say age greater than 18. That is true. Age is 24. But we're going to take the opposite of that, the not of that, and we're going to make that true become a false. And there's your explanation. It's false because age is greater than 18 is true, and we made it the opposite. Is the weight equivalent to 150? Well, that's false. The weight is 140. We take the opposite of that, or the negation of that, or the not operator, and then that now becomes true. Because weight is equivalent to 150 is false, we'll now make that true. That's two examples of how you could use the not operator in a Boolean expression. Truth table for operator and the ampersand, the double ampersand. That's the AND operator. We have two variables, P1 and P2. P1 is false, P2 is false. When we AND those two together, the overall results will be false. If we have P1 and P2, where they're false and true, when you AND them together, they will both be false. Likewise, if you have true and a false, the overall result will be false. The only time that you can have an overall resulting true is in an AND operator is when you have both operands, both P1 and P2, equal to true. So P1 ANDed with P2, a true ANDed with a true is going to be an overall true. They both have to be true in order for the overall result to be true using an AND operator. And here are some examples. I'm not going to go through all of them. Here's an OR operator. We have the same thing. We have the same scenarios. False, 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 true, false, false, true, true, false, and true, true. If you have P1 ORed with P2, a false or a false is going to be an overall false. A false or a true will be a true. All you need is one true for the overall result to be true in an OR operator. So we have one true here, so the overall result will be true. A true ORed with a false will be an overall true because we have one true here. And obviously two trues, a true ORed with a true, well, that's obviously going to be a true. And here are some examples you can look at. Okay, we have the exclusive OR. Here we have same situation, same scenarios. False, 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 true, true, false, true, true. P exclusive ORed with P1 exclusive ORed with P2 basically follows the same logic as the OR, except when they're both true, then it becomes false. So let's just step through this. A false exclusive OR with a false is an overall false. There is no true to any of this. A false exclusive OR with a true would be a true, because you have a true. You have just one. A true exclusive OR with a false would be an overall true, because you have this true here. A true exclusive OR with another true, you would think would be a true. In a regular OR, it would be, but in an exclusive OR, when you have two trues together, the overall result becomes a false. Excuse me, just one second. Okay, I'm back. I'm hoping nobody heard. Did anybody hear me coughing my head off? Okay, I guess you didn't. I'm going to use this mute button pretty quickly and have it on the trigger here. Okay, so that's the exclusive OR. It's a little tricky, and there are times when in programming you can use this exclusive OR. You will, however, find those other operators, logical operators, the and the not, and the or, used far more extensively. Let's look at a program, test Boolean operators. Okay, a nice short, sweet program. And we're going to get scanner input. And we're going to go ahead and ask for an integer. And the console operator will enter a number, an integer of some sort. First thing that happens here is we're going to take that number, whatever it may be, and do a modulus 2 on it and set it and say, is it equivalent to 0? And is the number modulus 3 equivalent to 0? So we've got some combinations going on here now with these Boolean operations. It's probably good to use some example data to follow it easier. I'll enter an integer. Let's say, what's a good one? How about 12? Okay, enter an integer. I put 12. 12 is divisible by 2 and 3. 12 is divisible by 2 or 3. I entered 12, so 12 modulus 2 equivalent to 0. That's true. This is an overall true right here. It's going to be ANDed with another Boolean expression. The left half is true. What about the right half? 12 modulus 3 equal to 0. Yes, 12 modulus 3 is equal to 0. So we have a true on the left-hand side and a true on the right-hand side. A true ANDed with a true is an overall true. Therefore, the program will execute the next sequential instruction. Next, 12 modulus 2 equivalent to 0? Yes, it is. It's true. I have that ORed with this piece, 12 modulus 3 equivalent to 0. That's also true. So I have a true or ORed with a true, and that will also yield an overall true. So this expression, this statement will get executed as a result of that expression, the large composite Boolean expression. And now we're going to print out the number is divisible by 2 or 3, which came out down here. The last one here, if number, which is 12, modulus 2 is equivalent to 0, okay, that's true, correct? 12 modulus 2 is equivalent to 0. I'm exclusive ORing that now with the second half of this expression inside the parentheses. And I'm saying is number modulus 3 equivalent to 0. That is true as well. So I've got a true on the left-hand side, exclusive ORed with a true on the right-hand side. True exclusive ORed with a true is going to be a false. So therefore, this statement here does not get executed. This one right there. It will skip over that statement and go to the next sequential instruction, which happens to be the end of our program, and the program ended as was expected after this statement. Okay, so here are some examples of where you can use these operators, including an exclusive OR, in combination. All right, let's try test Boolean operators. Okay, what do we got going here? We're getting scanner input. We're asking for an integer. We're going to put it into number, and then we're going to do the same. We just did this. We just did this. I guess I'm losing it here. 12. Yeah. All right. Moving right along. Oh, okay. I see. Okay. There's 2 slides with the same program on it. Okay. All right. Skipping along here. We're going to skip over. These are the bitwise. We don't need to spend much time on that. But here's an interesting little application of some Boolean logic here. This program determines leap year. Now, we think we know what leap year is. Leap year is, every 4th year, right? Well, it's not quite as simple as that. It's not every year that's divisible by 4. It's actually a little bit more complicated algorithm. This program first prompts the user to enter a year as an int value and checks if it is leap year. And it uses this very simple algorithm. A year is a leap year if it is divisible by 4, but not by 100, or it is divisible by 400. Okay, now how do you translate that over into code? Well, you need Boolean operators. And what we have here is a very long expression right here, okay, which will get evaluated to true or false, ORed with this expression right there. So all we need is this left side to be true, or this right side to be true. And if either are true, we have a Boolean. We have a leap year. And we can run the program just to show you how it works. No, I didn't open that. Okay. what's it called, leap year? Yeah, leap year. Okay, here it is. It's going to ask for the year, and it's going to use this big Boolean. We're going to get the year from the console, store it into the variable called year, and then we're going to go ahead and just declare a variable of the type Boolean. It's going to be called is leap year. You'll often see variables called is something or other, is leap year, is Tuesday, is springtime, and when you see that preceding is, that kind of indicates that this variable is a Boolean. It's going to have a value of only true or false. So this expression here is going to get evaluated, and it will get assigned into the variable is leap year. And that expression came directly from the PowerPoint. So we can pick any particular year. 2016 is a leap year. It is true. And all we do is we print it out and say 2016 is a leap year, and then we put the Boolean expression concatenated at the end of our system.out.println line, and we'll get true at the end. It gets a little tricky when you got like 2000. 2000 is a leap year. 2100 is not a leap year because of this Boolean expression on this side. So you can see how that works. So there's a real simple program that can solve a very complicated problem for people. Skipping over the lottery takes too long. Switch statements are pretty important. I'd like to go to an example of a switch statement. And I'll use the Chinese zodiac as an example. Okay, very simple program. It's essentially just using a switch statement. A switch statement comes in very handy when you have what look to be a series of ifs. And a better way to code a series of ifs so that it's easier to comprehend for not only yourself, but the next person that comes in and has to maintain your code would be to use a switch statement. And I would read up on it in the book. It's got some conditions that it has to adhere to, but essentially here's what we're going to use it for. We're asking for a year, and we'll put in a year, and we'll put it into the variable year. And then, using the switch statement on year, modulus 12, okay, so in other words, it's going to be whatever the year is, it's going to have, let's just run this. We'll do 2016 is the year of the monkey, according to the Chinese zodiac. And the way that works is it's using the modulus function to return the remainder. It's going to divide 2016 by 12, throw away the quotient, and return back the remainder. And evidently, the remainder was 0 for 2016. This must be divisible by 12. So as a result, it says the case is 0. So this will be a 0. This overall result in here will be 0. And it will execute this case and print out monkey. So it's the year of the monkey. The thing I want to stress is this important break statement. If you do not put this break statement in after where it hits the case that the condition exists upon, if you do not put this break statement in, it will step through each one of these cases and execute them. So you need to make sure you put a break statement in order to get out of this switch statement and continue on to the next sequential instruction. So that's a very easy way to go code something that without a switch statement, you'd have to use a series of ifs, which can get very complex, especially when you're using elses and else ifs and these other things. I'm going to skip over conditional operators and operator precedence. Applying operator precedence and associativity rule, the expression, we all know what the orders of operations are. It's PEMDAS, right? Parentheses, exponentiation, multiplication, division, addition, and subtraction. That's an oversimplified perspective. There's actually a lot more operators beyond just those handful represented in PEMDAS. And you can look at the appendix in the back of the book or look it up on Google it, and you can see that there are different levels of precedence. And a higher precedence will mandate that that get done before a lower precedence. So for instance, we know that multiplication and division have the same higher level of precedence as opposed to addition and subtraction. And we know parentheses is done at the highest level. So let's take a look at this big, long expression here in Java and understand how the actual computer will compute. The first thing that this will do in this expression is it will do the parentheses first. We have a plus sign, a multiplication greater than multiplication, parentheses, plus, and a minus. So we're going to do parentheses first and combine 4 plus 3 and make it 7. Now we have 7 down here. Now we got a plus, a multiplication, a greater than sign, a multiplication, and a minus sign. Well, multiplication gets next. So we're going to do 4 times 4. There are 2 multiplications, one here and one here. It will go from left to right. So we have this multiplication and this multiplication. The computer will do this one first and come up with 16. Now we have 3 plus 16 greater than 5 times 7 minus 1. Well, we got a plus, a greater than, a multiplication, that's the highest order so far, and the minus. So we're going to do this next and come up with 35. And now we have a plus, a greater than, and a minus sign. What gets executed next is the plus, because it is the same level of precedence as the minus. When that's the case, it goes left to right. So we'll do the left one first, and it will combine 3 and 16, get 19. We have a greater than sign, and 35 minus 1. Well, a minus sign gets done next, so we got 34. And now we have 19 greater than 34. This is going to get evaluated, and we're going to say is 19 greater than 34. This overall expression, the result will become false. So that's exactly how the computer does these rather complex, convoluted Boolean expressions using multiple operators of different types.
Can I ask a quick question?
Sure, go ahead.
The example, 2 lines up, 3 plus 16 and 35 minus 1, had the signs been switched and the subtraction sign been in front and addition in the back, it still would have read left to right and did the subtraction before the addition?
Yes.
Okay.
They're identical in the level. Okay, and there's a chart. There's a chart you can take a look at, and they actually quantify the level of precedence with a number. and the number that's quantified for addition is the same number as subtraction. And
Gotcha.
likewise,
So it's not exactly like PEMDAS.
it's not exactly like PEMDAS, right? And people oftentimes
Okay.
literally use PEMDAS and say, oh, well, does that mean multiplication is always before division because M comes before D? No, that's not true. The computer, the way it computes, is going to go with these levels of precedence and associativity rules.
Beautiful. Thank you.
Okay, good. Good question. All right, good. I think I'm not going to talk too much about debugging. Hopefully you're getting a full exposure into debugging. The code that we're starting to write now is getting a little bit more challenging, and I'm sure you're getting all these different types of bugs and errors and logic errors and compile errors and things like that, and you're getting comfortable with NetBeans. And you can always put in a system.out.println, open paren, and put the variable name in and see what's inside the variable and see what you're getting, and then do it step by step by step. And if you have a big, long expression, comment it out and just do one piece of the expression and print it out. Then add a second piece and print it out, and add a third piece. And maybe the third piece is where you're making your error. So now it's a process of elimination. You're basically ruling out things to zero in on where you find the error. But debugging is a bit of an art, and it takes time. And there are tools in NetBeans. I'm not going to go through them, certainly not on a webinar, but you can go explore up in the toolbar up at the top, and there are debugging tools where you can actually set breakpoints and stop the processing and see what the contents of all the variables are at any particular point during the processing of your program. Okay, that brings me to the end of chapter 3. I want to go over your lab because it's a little bit more challenging. And definitely do not wait until the end. This is what, Thursday? So don't wait until Monday at 11 o'clock at night to try and tackle this one. You'll frustrate yourself pretty quickly. Again, this is one that you may want to take in pieces. I called it sorting 3 odd and even integers. I want you to use decision statements, which are if statements, and logical operators only. I put that in big, bold, black, underlined letters because oftentimes students will go ahead and apply Chapter 8 to solve Chapter 3's problems. And I'm not going to permit that. I'm not going to give you credit for that. You have the tools at your disposal up through Chapter 3 to solve this problem. I want you to build the fundamentals, the logical fundamentals in your brain to solve these problems. Later on, we can find out ways in which to use loops and arrays and other methods that are already built for us, formatting methods, things like that. But for right now, if we have not discussed it and it has not been brought up in the chapters that we've discussed, I do not want you to use them. So this assignment is going to be using decision statements and logical operators only. Create a Java application in NetBeans called Lab 3 that asks the end user, please enter an integer between 0 and 99. And next, enter another integer between 0 and 99. All right, so the user is going to enter 2 integers. Let's say 20 and 40. The program will reject any entries that are less than 0 and greater than 99. All right, sounds like an if statement. If the entry is less than 0 or the entry is less than or greater than 99, then print out a message. So those are some if and ors. If there are 2 incorrect entries per entry request, the program will end using the return statement. So if you get 2 in a row, obviously the end user is not reading, and you can just end the program. And the way you can end the program right then and there is just to type in return with a semicolon, and it ends the program.
I have a question, Professor.
Yes, go ahead. Yes, go ahead.
In the book, there is an example of one of the programs that uses the system exit method in Chapter 3.
Yep.
Is it the same thing to use that, or should we use the return statement, particularly in this case?
Great question, Julio. I try to expose you guys to as much as I possibly can with regards to programming. So yes, the book uses a system.exit with a return code 0. Now I want to introduce to you just a straight return. And the difference is, sometimes what happens is when you return control from your program back to the operating system, oftentimes the operating system wants to know, how did that program end? Did it end happily or did it end miserably? And you can go ahead and put exit with a return code 0, 1, 2, 3, and then those numbers that get passed back to the system, back to the operating system, they can be interpreted as, is this a severe crash of the program that just had control, or is this a slow, is this a return back that's not a problem at all? So that's the difference basically between the two. A return, so it's a straight return, would not give the operating system any indication as to the reason why it returned. Okay?
Okay, got it. Yep, thanks.
Okay. Okay, so if you get 2 in a row, you issue the return statement. The program will then generate 3 random integers within that range. What range did I say? I think I put in 20 and 40. So I want you to generate 3 random integers between 20 and 40, whatever the 2 integers then that I put in it between that range. You can do that using the following formula. I gave you the formula. This is actually pretty neat. You can generate an integer, a random integer, if you go ahead and code whatever the min is. So in my case, it would be 20, plus we're going to cast to an integer. We're going to use the math.random method with nothing inside, times open paren, max minus min, that's 40 minus 20, plus 1, close paren, semicolon. That whole thing will generate a random integer between 20 and 40. You can do that for integer 1, integer 2, and integer 3. I'm asking you to generate 3 random integers. So to do 1, use this. You could call it integer 1. Do it again for integer 2, and then do it a third time for integer 3. Same exact code. All right here. The program will then sort them. So I don't know, let's say we picked, 25, 30, and 32. I'll probably never remember those. Okay, the program will then sort them in ascending order. So what did I say, 20, 30, and 32. So it's already in ascending order. But if they didn't come in, then it would get sorted into ascending order. You need to use decision statements. Okay, you cannot use sort methods or anything else. You have to use decision statements to create the ascending sort for these 3 numbers. And then output them to the console in ascending order on separate lines. Here's the pseudocode to go ahead and sort these 3 integers. If integer 1 is greater than integer 2, swap the 2 values. Then, if integer 2 is greater than integer 3, swap those values. Then, if integer 1 is greater than integer 2, swap those values. If you do those 3 steps, the 3 integers will be sorted in ascending order. You will need to declare a hold variable to hold one of these integers while you swap the values. Kind of like what we did before when we flip-flopped the subtraction game. We have to place one value in a temporary hold area. Next to each integer, you will next to each integer will be even or odd, depending upon the value of the integer. Now, when you're doing this, it's complicated, okay? And I'm telling you, make sure you test every combination of random integers coming in. That can be small, medium, or large. And I just kind of broke out all the different combinations. You can have small, medium, large, small, large, medium, medium, small, large, medium, large, small, large, small, medium, and large, medium, small. And you should go and make sure that you test every one of those scenarios to make sure that your logic will eventually wind up sorting them in ascending order, 7, 8, and 9. I use these as examples. Finally, calculate the sum, the product, and the quotient, integer 1 divided by integer 2 divided by integer 3 of the three integers, and put them to the console. Be sure to check all calculations and make sure that they are accurate. Here's a sample console output. Please enter an integer between 0 and 99. I didn't read my instructions and I put in -1. The program comes back out and says, outside the range, please enter an integer between 0 and 99. I put 100. I'm still not reading. That's my second strike. I'm out. And I'm using if statements. No loops, if statements. I made 2 mistakes. It says outside the range, program ending. That's where I issue my return statement. Now, here's where I go ahead and use the use correct entries. Please enter an integer between 0 and 99. I'm still not reading my instructions, and I put in -1. It says outside the range, please enter an integer between 0 and 99. I finally got it. I put in 80. That's between 0 and 99. It accepts it, and it says next, enter another integer between 0 and 99. Okay, I put in 20. What did I put in? No, I put in 100, and it didn't like it. So it said outside the range, please enter another between 0 and 99. Then I figured it out, and I said 20. All right, so now I have my range. It's 80 to 20. I want you to print out the range, but I want the range to be in ascending order. I don't want you to say the range begins at 80 and ends at 20. I want you to say the range begins at 20 and ends at 80. So for each of those numbers coming in, you're going to have to determine which one is bigger and which one is smaller, and then put the smaller one first and the larger one last in this output statement. Next, the 3 sorted random integers between 20 and 80 are, and now you're going to generate 3 using this this method right up here. You're going to go ahead and generate 3 random integers. In my case, I generated 20, maybe 48, 21, and 80 in that order. I need to sort those. And the way to sort them is to use that algorithm that I gave you up above. And now they're sorted, and I need to go ahead and put next to them whether they're odd or even. And the way you can do that is right after you put out the number, you could go ahead and do the modulus function, modulus 2 function, equal to 0. And if it's true, it's even. Otherwise, it's odd. So that's a little tip there. Then you go ahead and you take these 3 integers and you take the sum, add them together, multiply them together, and put out the product of 21, 48, and 80 is that large number. And the quotient is going to be integer 1 divided by integer 2 divided by integer 3. And I got this crazy fraction right here. Now you may be thinking, this is all integer division. Well, what you may want to do is declare a variable called quotient of the type double, and then do this calculation and have integer 1 times 1.0 divided by integer 2 times 1.0 divided by integer 3 times 1.0 in order to get precise division. Otherwise, we know with integer division, you're going to get very imprecise results. And I'm looking for precise results for my quotient. You must also
I have a
use
question, Professor.
Yep, go ahead.
Is it necessary to multiply all three by 1.0 rather than just the first one, the leftmost, since it becomes a double, and then when you divide by integer 2, it stays a double. Any subsequent divisions will stay a double.
Okay, well, test it, okay? Test it. I don't want to say yes and I don't want to say no, but it's my belief, because you don't necessarily know whether or not you're going to get a double. It's always safe to go ahead and do the 1.0, multiply times 1.0, and then you know you're dealing with a double.
Okay.
Okay?
Now, is it okay, so just to do one variable as opposed to the flow chart in which you had three different ones?
For integers?
For the quotient,
I think my solution, I used a few variables. I think I used quotient 1 is equal to int 1 times 1.0 divided by int 2 times 1.0.
Yes, and then you did quotient 2 and then quotient 3.
Right, right.
Yes, something like
that. I did it in steps. I try to keep it as simple to follow as possible. You can go ahead and rewrite people's code and make it the most, you'd be pulling your hair out trying to figure out what they're doing, unless they commented correctly. But I try to write my code such that the normal programmer coming in after me can go ahead and figure out what I'm doing. So that's what I did. I would create, you call them work variables. They're variables that never get put out, but they're used to go ahead and store data done by other calculations, and then you use those work variables to eventually feed a variable that you're going to print out.
Okay.
Okay?
Got it. Yep.
Okay. You must also use proper naming conventions for all variables. I want you to start using real good programming habits. As these assignments get more and more complicated, like the restaurant bill, you need to start making sure that your variable names are crisp and that you use the proper casing, the camel casing. So make sure you use proper naming conventions for all variables. Include a program header documentation block. Use block comments and line comments. Make your code look very good. Indent things properly. Space where you need to space. I'll leave it up to you. And zip your Lab 3 folder and you got the drill from here, right? Call it your name, lab3.zip, and send it to me as an attachment in Blackboard. I also gave you the flowchart for this, which should be very helpful. I'll make this larger. Going through this, let's see. We're getting input, and we're looking to see if it's less than 0 or greater than 99. If it's true, you're going to ask again, and if you get another bad one, you exit the loop. But if you get a good number between 0 and 99, you're going to go ahead and ask for another input, input 2. These are just variables names that I used in Visual Logic. And do the same thing. So this segment of flowchart is pretty much identical to this one here. We're going to go ahead and see whether or not the second integer that I got from the console is between 0 and 99. If it isn't, we're going to ask the question twice. If you don't answer it right, we're going to exit the loop. Otherwise, at this point right here, I now know I have a good range. The range I used was 80 and 20. Now you got to ask, is 80 less than 20? Is input 1 less than input 2? And if it is, you got to make sure that min, the variable min, has the smaller one in it, and max has the larger one in it. If it's false, you have to make sure that you assign the right inputs into the appropriate max and min. Then we have down here, we're doing that big calculation. Int 1 is equal to the min, that whole thing, random, whatever. And so now we're going to get 3 random integers between that narrowed range, 80 and 20. Int 1, int 2, and int 3. If int 1 is greater than int 2, we're going to flip-flop them. If int 2 is greater than int 3, we're going to flip-flop them. And here's the 3 steps to do. Create a temporary variable to store int 2, then move int 3 into int 2, and then take the temporary and put it back into int 3. And then the third step is if int 1 is greater than int 2, then flip-flop them again. The range begins at min and ends at max. So now we've calculated that all out, and now that gets put out. And the 3 sorted integers between min and max are, and if you follow my flow chart, it goes to over here. And we have where I do my modulus function, my modulus 2 function on int 1. If it's equal to 0, well, then it's even, and I put out even. For the second integer, I do a modulus 2. If it's even, it's even. And if the third integer, if it's even, I put out even. Otherwise, I'm putting out the integer is odd. And then the last piece is just doing the sum, the product. And here's where I did quotient 1, quotient 2, and this is like, I'll call it the master quotient, the overall quotient that's going to be put out. These are work variables, quotient 1 and quotient 2. So quotient now gets calculated. And then I put out the sum is this, the product is whatever the product is, and the quotient is that. So hopefully this flow chart will help you in tackling this problem. And I wouldn't suggest you sit down all at once and try and write this program. Do it in pieces. You may want to do this piece first, or these first few pieces, and then take a break, and then go ahead and tackle the next piece, and then the final piece. Okay, that's your lab 3. Does anybody have any questions?
I have one last question, Professor. This is Julio again.
Yes.
The naming of the project, you want us to give it a specific name. Should the same be for the package and the main class?
Okay, here's what you need to do. When you go into NetBeans, you're going to go do new project. It's going to be a Java application, and up at the top, it's going to ask you for it'll pre-number something, Java application 20, 22, whatever the heck you're up to.
Yes.
Change that to be lab 3, uppercase L, AB03. All right, and then just prompt your way all the way through, and then you'll finally get the package created with the right name. The package will be lowercase lab 3. You write your code.
So you want to have the package and the main class the same name as the project.
Yes. And then when you go ahead and you get out of NetBeans, you stored it wherever you said you were when you were creating your Java application. You go to that place where you stored it, and that's a big folder. And what I'd like you to do is to zip that folder, right-click, and send to compressed zip file. And then that'll now be lab3.zip. And then do right-click, rename, and call it Julio lab3.zip. And then you attach that in Blackboard. Okay?
Okay. Yep. Thank you.
Okay. Any other questions? Okay, well, if that's all we got, then I'm going to call it a night. Thank you guys for participating, and we will talk again soon. Good night now.
Good night.